apágalo mientras no hables porque se ve. No va bien.
Entonces, mi colega nos la pone ahora.
Sí, sí, tú tranquilo.
Tranquilo.
Sí, él le da a presentar.
No, yo tengo a... ¿Lo tienes ahí?
Pero luego me lo llevo. Tendrás que espabilarte.
El puntero.
Hay uno ya. No, no, eso no lo puedes poner. No, enchufar, no puedes enchufarle nada.
No enchufes nada. Vale.
El que hay uno hay un pasado.
Bueno,
Ya estamos ahí.
pero eso.
A lo que vamos. Hello everybody. Good morning and welcome to the second day of the Photonic Integration Week. We're going to start the session of this morning. It's about industrial chairs and over the PERTE program. And our first speaker is Francisco Díaz from Universidad de Vigo. So, welcome. Go ahead.
Okay, thank you very much. First of all, thank you very much. I want to thank the organizers for inviting me to give this talk today. I'm going to save time because I am only going to give an overall description of this cathedra chip that we submitted last year. And the idea for us is to organize a double role for this cathedra. First, a training, an intensive training, not an official master or PhD degree, but more a title from the University of Vigo, but intended mainly for industry, not for academia mainly. This is one role, and the other one is an R&D project that I'm going to describe right now. So the motto or the motivation for this cathedra is to train people that we need really skilled people in integrated photonics for coming years, and also to deliver some outcomes related to what we foresee in the future of electronic and photonic integration, we can say. So we gave this name, Open Access Testing of Next Generation Photonic and Electronic Chips, and the acronym for this is Next Chip. So this is the name. So as I was explaining, our idea for the future of photonics is to encompass in a single substrate or PCB using interposers different chips that will be on top of this substrate. So we can have different 3, 5, or 4 group semiconductors, and the idea is that you can organize yourself a integrated circuit, not only for photonics, but could be for electronics and photonics. So we see this is in a medium term. Right now we have a lot of R&D in gallium nitride on silicon, for instance, in the future indium phosphide on silicon. There are several attempts for integration, 3-5 on silicon nitride, 3-5 on silicon. And the idea is that that probably all the main players in this field will use the 2.5 or 3D integration concept coming from microelectronics and deliver it to photonics. So this is the goal. And the goal for the cátedra is to have, first, in the R&D domain, a new generation of a wafer-level testing tool, a quick testing tool for wafers. I'm going to describe it right now. For high temperature, high power, different materials, and also to prepare what we call a testing design kit, just to standardize somehow, as we have the PDK or ADK at TDK too. And then the training for people, because we are going to train 20 people per year in these cathedrals. So going back, we have these partners in the cathedra. Some of them are going to be partners only for training, others are going to be partners in the R&D also project. So of course we have the university that will provide all the infrastructure for the training. Also to hire the researchers to do the testing tool. But also we have some companies like Keysight, IceCom Datatech, MPI, that will provide also equipment and work with the university in the R&D project. We have also Spark, Navantia, Monodon by Navantia, Alluvia Photonics, ICFO, Tyndall, National Institute, and then Gradient and IMEN, that are the ICT and the metallurgic sector technological centers in Galicia. Well, this testing tool will be designed to cover a wide range of measurements and also materials. So the idea is that we will deliver this at the end of the project. This will be the main outcome of this R&D project, apart from this TDK or the testing design kit. So we will be able to provide low frequency electrical measurements with more than 20 electrical probes, high frequency electrical measurements also up to 100 gigahertz with more than 2 high frequency probes, high frequency and high temperature measurements up to 40 gigahertz, and different light coupling methods also within and off the chip. So the idea is that this tool will also have surrounding them equipment to fully characterize a photonic chip, going from 400 nanometers to 1.7 microns. And the idea is that this will be useful not only for a single compound like Ne3.5, like indium phosphide, gallium nitride, gallium arsenide, but also for silicon, and to do it quickly. The idea is to also have a relatively high speed doing these measurements. As you know, the different measurements for different materials. This is something rather difficult. But right now we think that an improvement can be made joining all of them in a single tool. So in order to provide this outcome, we will demonstrate these capabilities with these companies or centers, research institutions, in 7 different applications. One is typically fiber optic telecommunications in 400 gigabits per second transceivers. Second, high-speed, high-power electronic chips. The PDK, that will be done by Alluvia Photonics. The application in augmented reality or virtual reality glasses. Application in the area of quantum with ICFO. Application of LiDAR with actually, it's LiDAR not for autonomous vehicles, or this is for robotics mainly. An application in underwater communication. Just some of them are really low TRL, others are more in the TRL from 7 to 9. In terms of the impact, we are going to hire 3 postdocs, 6 PhD students, and 2 engineers to work in this project along the life cycle of this catheter of next chip. 50% will be women. So this is our goal. And we will have at the end of the project 25 contracts in all these companies. Some of them are right now starting photonics departments like Gradient or Navantia or even IMEN. So we have the commitment of hiring these people at the end of the project. In terms of the training in these cathedrals, we will provide a 7-month intensive training. We won't have any official academic degree here. And then we will cover not the whole value chain, but mainly we will have an specialization in testing, because this is the objective of the cátedra, in testing and packaging, but we will cover from the theory of electromagnetics to photonic IC design and testing, clean room fabrication. Then we have also some agreements with INL, with IMEC, and with other clean rooms, so we can provide, in some cases, dedicated training in clean room, packaging, testing tool anti-decay that will be delivered by Spark, transferable skills, because we also consider that these researchers at the end of the project, they need to know how to manage a project, how to apply for European projects, how to make a good speech, not like mine here. So we think that we need these transferable skills from the very beginning, and also on quantum photonic technologies. So the idea is to enroll 20 master students per year, re-skilling people. We are not going to restrict that they can be telecommunication engineers or physicists or whatever, so we can have industrial engineers. 5 grants per year will be given by some of these companies to continue pursuing the PhD thesis. 5 grants will be dedicated for women. And then we will also provide some activities to promote gender balance, like what we call reactivity, is going back to photonics. Some women that are right now working in companies that had previously a degree in some of these fields, but are not working in the field right now, but would like to come back to work in this field. We will have also what we call meet-integrated photonics, that is something for high school students, specifically for women, and also a podcast where we will interview well-known and really high-skilled women that are right now working in photonics all over the world. Because we think also that women need some references to come to this career. As we all know, there is a lack of women in the technical field, so we think we need to do something in these aspects. Okay. So this is the chronogram. I'm not going to get into the details of this chronogram, but well, right now we spent 1 year. The first year probably is over, so we are going to work on the last 3 years. And as you can see, the last one, the blue one in the low row of this picture, is the training that will be 7 months, during 7 months, and while at the same time the top rows of this Gantt are the rows dedicated to the R&D project. In terms of the organization of the cátedra, there are 2 chairs. It's Francisco Díaz, so myself, and the other chair is Sonia García Blanco, that is full professor at the University of Twente, Mesa Plus, so probably you know her, and we have a board that will have different roles in terms of the scientific and also the academic aspects, and also to provide some guidance about the future of this cátedra at the end of the project. So we have the Vice Rector of Research, Belén Rubio of the University of Vigo, Luis Torner from ICFO, Francisco Soares, that is the CTO of Spark, Luis Pérez, that is the director of Uradian, the ICT Technological Center in Galicia, and also José Manuel Silva, that is former General Director of Research of the European Commission. And we also have a specific training manager, that is Carlos Mosquera, full professor also at the University of Vigo. He's been one of the founders of Uradian and former director of the research center in the University Atlantic Research Center. So we have, as I said, in this board we will assign different roles for the scientific and training board, and also we will have a company specialized in dissemination and communication, because we think it's not only important to do what we are going to do, but also to communicate what we are doing to the society and giving back the outcomes to the society and to different media, from a general audience to the politicians, or also to companies, and also to the people like you. This is the first communication activity, for instance. And I think that's all. Thank you very much.
Thank you very much. It's not working. It's on. Sorry, I think you can hear me very well. So, any question in the audience? No questions in the audience? Yeah, couple actually. So, thanks of course for presenting your project. The question you have your partner Axcom at that, I think. So my question was, do you have already a partner that is developing the tool, the wafer prober, or you will start with a commercial tool already?
No, we will start with commercial tools. So we are going to join capacities from existing tools, both in the software domain, but also in the hardware domain. So joining Keysight plus ISCOM Datatech plus others. So this is open still. That could join the cátedra to develop this tool, to produce this tool in the end.
But that's a question. Are you going to start from scratch, like a
No,
or you start from a vendor already?
No, we start from a vendor already.
Okay. And wafer sizes you're targeting?
6 inches.
Any other question?
It's an optical probe. But it's, yesterday we were discussing about this nano printing of lenses on fibers to be able to do edge coupling. And this is for grating couplers, or is also intended to be edge coupled?
It could be grating and edge coupling, yes.
Okay.
Thank you for your talk, Francisco. Yeah. I'm Ernesto Barrera from Photonic, company that provides substrates, wafers, silicon wafers, and we represent several equipment manufacturers for all semiconductor front-end processes. My question is related to the academic program you're proposing. What kind of skills and aptitude the students will acquire, and what are you targeting for the future? I mean, what kind of industry they can go through?
Well, when we were thinking about this academic title, we thought that we cannot specialize in something really specific, because in that sense we don't want to have overlaps with other cátedras that could be here. Of course, we are collaborating with all of them, with all the ones that are going to give these talks later. So the idea is to have a broad overview of the whole value chain, from the theory of electromagnetics, design and simulation, fabrication techniques, testing and characterization, and even some certification, and other collaterals like quantum, artificial intelligence, and machine learning. So these techniques apply to photonics, but we are going to specialize them in testing and packaging. This is what we want.
Okay,
I
thanks.
don't know if I replied. Okay.
Okay, if there are no more questions, let's thank again the speaker.
Vale.
So our second speaker of today is Guillermo Carpintero, and he's going to show us the industrial chair of Universidad Carlos III from Madrid. Thank you.
Thank you very much for the invitation. It was a great idea to organize this session in this forum, so thank you very much, and it's always a pleasure to be back in Valencia. Actually, initially the talk was this chair on advanced test assembly and packaging. Actually, if you go to the press release in University Carlos III, we have actually 2 chairs that have been granted. One is on, actually the 2 are EPIC with different type of ratings. So we are the EPIC chairs. And the first one is in quantum. I asked Cristina a few slides to present it as well, so for completeness to all of you. This chair is actually aiming at different quantum aspects, quantum key distribution and quantum sensing. It's actually involving these areas that just mentioned, different aspects of quantum technology, and is actually headed by Cristina de Dios and different groups in the university, together with Archimea. And at the end, their training is going to be embedded into the degrees that we have at bachelor and master levels. Bachelor is engineering physics, and we have a master program in quantum technologies in the university. So this is as much as I can say about this. The other chair is the one that I'm chairing, which is in packaging technologies. This is with a number of industry. Actually, there are 2 photonics companies, which is VLC and Omatidia. We have as well terahertz high frequency. This is not just optics, packaging of optics chips. This is packaging of optics and for electronics. We have Das Nano, is a leading company in terahertz sensors. They have recently earned contracts with Volkswagen for quality control, and Leapwave, which is a spin-off of GC3M, in which I am involved in high frequency probes. In addition to that, we have Keysight and Nanoscribe. Actually, Nanoscribe is a fundamental enabler with 3D printing, actually to couple the radiation. Why we are doing this? Basically because a chip is just a chip. It's not something you can sell. Actually, there are a few of us that buy chips and try to assemble and work with them. Because after that, there is a whole chain of things that you have to do. As was mentioned yesterday by Peter O'Brien, it's hard to do because it takes a long development time. It's knowledge, not IP. And there seems to be less value on that, but nevertheless is key technology. And the problem as well is that if you try to package something you design, you are doing things the other way around. You have to design for the packaging. And this is what we are trying to address in this chair. And actually, it's always, I added this cost structure, I think it's from a slide from Peter O'Brien years ago. And it was always said that, okay, the problem of photonic integrated circuits is that you have to package them. And for electronics, that's easy. And it's easy until you consider that the high frequency. In high frequency, the electronics behaves as waves, and they have the same problems as we have in photonics. It's a different scale, but it's the same problem. And that's why the cost in microelectronics seems to be low until you start considering high frequency. And by high frequency, I mean gigahertz, above 60 gigahertz. Because above 60 gigahertz, there is a specialized equipment to be for the testing. There are not even probes above 110. There is only one manufacturer that does probes above 110. So our chair is basically aiming at packaging at high frequencies, above 100 gigahertz, additive manufacturing, and materials, because in RF, materials are a killer. And when I say killer, is killer real. It's light, because actually kills the signals by the absorption of the materials. And then we have as well artificial intelligence and artificial vision to make automation of the assembly, because that's the only way that we can address this. And the three groups that are involved in this is my group, Optoelectronics and Laser Technology, Synthesis and Processing Materials, because these are the guys that are going to collaborate with us to provide all the training in epoxies and different types of fabrication. And then the Intelligent Systems Labs, of course, they are the ones that put the brains into this. Why I was stressing about the high frequency, because if you go to the market and look for packages, the ones that you can see go up to 64, and that's the maximum. There is no one that will do a package unless you pay them a sufficient amount of money. And the problem about it is that if you see on the graph on your right-hand side, the problem is that at high frequencies you don't even have connectors for the packages. Between the chips you can say, okay, we have wire bonding and there is flip chip and there are things that I can do. But for the package, there is nothing. You can either go to coaxial up to 110. I just put the 220 there, but it's just irreal because it's not commercialized. It's just a solution for 220 probes. And then above that, you have rectangular waveguides, and it's not continuous. So you can take all the people doing spectroscopy and tell them, no, you are not going to package your thing. Our idea is we want to do that. We want to be able to bring into the market new type of connectors and interconnects that will cover at least up to 300. If you ask me what for, spectroscopy, that's one thing, and the other thing is 6G communications, which they are not going to go into the terahertz range, but certainly they are aiming at least to reach into the hundreds. And then in the optical, if you go to the optical, and this is why we have Nanoscribe as a partner in the chair, is because there is a new type of interconnects. The photonic wire bond is one interesting example that allows you to make interconnects. When you start looking at the details, it's much more complicated because then you are asked to start having problems about, the height difference is not as much as you want, the spacing in between the chips is not as much as you want, so there are a lot of limitations involved in this, even if it looks very nice and that will simplify life. No, has requirements. And all these things is what we want to introduce in this chair. And the other part, which is really interesting, is about doing 3D printed lenses. And the 3D printed lenses, the advantage is that it not only works for optics, but also works for the electromagnetics, for the RF. And, that's, and that has involved some material science into it. And that's why we have all these ingredients, we mix them. And at the end, what we are here for? Well, we are going to have positions, PhD positions, postdoc positions, and actually one technician. And where we are aiming to put this is part of the plan that we can now start with, is to create an institute in which this chair, which is interdepartmental, interdisciplinary, multidisciplinary, or whatever you want to call it, to have a common umbrella for all of us. And what we are aiming to do is not support our training programs and degrees. This is a program to support industries. This is a program in which what we aim is to have a title, UC3M title. We are not going to go yet to accredit this in the national accreditation offices. We are going to do a program that is aimed to cover the needs of industry, so we are not going to bother with the academic part. We are going to aim to train people to how to use the machine. What I mentioned, all these requirements of, if you want to use this technology, you have these requirements. That's what we want to train. This is what we are aiming to teach. So people know when they are going to use a technology, know what that technology requires. And on that part, that is what this degree will do. Maybe we will have also separate courses to certify people to use the equipment. And then companies will be able to come to our premises and use the machines themselves instead of having a technician to which they have to explain what they want to do in machine, and that might involve disclosing information they don't want to, because in packaging, the processes are the IP, and usually they are kept as industrial secret. We have two running projects that are also supporting this. Terra 6G, which I coordinate, is a 6G SNS project, and Polynices, which is an industrial leadership European project, and they are hybrid integration. And 4 terahertz, millimeter wave communications. And this is where we ended up that there is a bottleneck in packaging. Not even packaging partners are encountering surprises when they do this. And I think this is it.
Thanks a lot, Guillermo. Any question from the audience? You're too shy this morning.
I cannot ask myself.
No. I have questions for you, don't worry.
I do worry.
The very basic question I have is, you say that the target is like high-speed RF signals, so beyond 60, 70 to hundreds of gigahertz. What would be the main application for this in photonics today?
As I mentioned, definitely there is wireless communications, because in wireless communications, if you think about connecting network to clients, that's going to be not high speed. But deployment of small cells is being considered in hotspots. And actually, you can also, if you provide carrier companies with a way in which they don't have to put fiber and it's a small size, because that's why we are doing this in photonic integration, because we want to reduce the size of, if you give them a small form factor transceivers in which they don't have to rent a space, they'll be carrying you on their shoulders. The other is spectroscopy. There are applications. Das Nano has made a use case in the automotive industry to measure the thickness of paint in cars, and they need to scan across different frequencies. And there are the other application is if you want to use, now it's a hot topic, the ISAC, the Integrated Sensing and Communications. And there you need broad bandwidth, because you either use your bandwidth for communications or you use it for radar. And you might need, for radar, you might need some frequencies. For communications, you might need other frequencies that are not far apart in the spectrum. If they are so far apart that they don't fall within the frequency bands of rectangular waveguide, then you have a problem. And the other hand is that if you are setting now a communication link for 6G, 5G, and you want to make it future-proof. You just you know that okay, what frequency I make it work? Do I work in the E-band, or should I move to 100 gigahertz? The idea is to provide an interface that covers all the frequencies being used today and that are being considered in the 6G vision that it's being developed right now.
Okay. Thank you. Any other question?
Hi. Thank you, Guillermo, for your talk. Just one quick question. Which is the time frame you have in mind to develop this platform?
Well, considering that we've been working on these European projects for more than 10 years, we already have some equipment. Actually, the picture that I showed here is, well, actually that's Musin. It's a postdoc, which is in the spin-off company. He's been working assembly 300 gigahertz transmitters. That's what he's holding in his hand is such an emitter from that works from about 50 gigahertz up to 300 gigahertz. We've already developed know-how and technology, and we have already some equipment. So the time frame is that we will have the equipment. Actually, we already have equipment today to start, wire bonding, pick and place, fiber aligner, and the last equipment will come financed by this chair, which is a nanoscribe printer. And the idea is that that will be in place 2025. So I think we will have everything to start these trainings next year.
Okay, really nice. Congratulations.
Well, thank you. Thank you very much. All companies will be welcome to use it, because actually the idea is that this equipment is not sitting in the lab, but hopefully we cannot say it's going to be used 24/7, because with the current labor law, we cannot put someone to work in round shifts in the university. But the idea would be to use it as much as possible. And also the idea as well is to collaborate with other packaging companies. So our facility is learn the machines, see what the processes, the process requirements are, and also connect with other packaging companies, because this is a prototyping facility. Scale up should be done later on, and we will have to connect with, of course, with Tyndall, that it's already invited, and with other packaging companies that we know are out there. Okay.
Okay, thanks a lot, Guillermo. So our next speaker is Íñigo Molina. He's going to show the industrial chair of Universidad de Málaga. So the floor is yours.
Okay, thank you. Thank you very much. Thank you very much for inviting me to give this talk. I will talk about this activity in the Málaga Cátedra PERTE chip. I think my approach, or our approach to this, is rather different than the one that I have been seeing in the last presentations. Okay, we understood this as a tool to strengthen the ecosystem in Málaga, in Photonics Málaga. So what I'm going to do here is to show you which is that ecosystem and which are the tools that we have implemented to try to push that ecosystem. Okay. So when I was last here in 2022, I presented this. That was the group. We were there, seven professors in the ETSI Telecomunicación doing applied research in photonics. That was the group in 2022. Okay. Then we just had founded a new company, which was Bioherent, that was started from the PhD of Jonas Lewerman. He gave a talk yesterday. It is a collaboration between allergy group, an allergy group, a chemistry group, and photonics, and we are doing IVD allergy diagnosis. It had 5 employees. Okay, so that was 2 years ago. So I'm proud to say that we have evolved a little bit. So now what I call, okay, it's maybe too much, but it's what I call Malaga Photonics ecosystem now in 2020-24 is again my research group, the Photonics and Radio Frequency Lab, also Bioherent, that were already there 2 years ago. But now you see the numbers, instead of 7 professors, we are 11, okay? So that's really nice because we are 11 persons completely dedicated to integrated photonics, okay? That means 3 full professors, like 4 or 5 titulares de universidad, and the rest are profesores ayudantes. So it's quite big. So Bioherent has gone from 5 to 15, which is not bad either, okay? Now they are moving, okay? You saw yesterday some of the achievements. I will show something else there. And then there was, in the picture before, there was another PhD student that now has become, again, the co-founder of a new company, which is AG Photonics, okay? Which is now 4 persons, which is not bad, okay? And all this, we have got this because we have the commitment of Bundnet Capital. We have established very good connection with them. I think we see the problems in a very long run term, which is quite difficult for an investor, okay? And now what we are trying to do also in this category a little bit is to join with other forces in their surroundings in Malaga, which are the microelectronics sector. And we are doing this a little bit around cathedral apprenticeship. This is the first experiment, let's say, okay? So in cathedral apprenticeship, we will be collaborating with, of course, the university, but also with this institution that is in Nova RV. Mario Nemirovsky was coming yesterday. Unfortunately, he lost the plane. And the Malaga Technological Park, which has started to look at the photonics as a very interesting way to improve in their capabilities. So I don't know, maybe you already know a little bit about my group, okay? So I'm going to put a little bit in this ecosystem, these 3 legs of the ecosystem, what we do. So our expertise is in coherent receivers for telecommunications with a very big job there in the past. We are really reputed people in subwavelength-based silicon photonics. This is the topic mainly that we work. We use metamaterial-based waveguides for everything to do high-performance devices. We are usually looking at dB performances, etc. We have also a lot of activity in sensing. Specifically, we use the concepts inherited from there for coherent sensing. That is what Bioherent is using, okay? And we also did a lot of work in platforms for mid-infrared with Cornerstone. And, well, we recently brought to Malaga to Diego, who many of you know. He was working here in Valencia, and he brings a lot of expertise in microwave photonics, which is not one of the big activities in the group until now, but we hope it to increase, okay? Okay, and the approach of the group is always the same. Okay, we are photonic integrated circuit designers. We are fabless approach, okay? We do design, we have characterization, but not fabrication. We don't have technology, and we are very much engineering approach. I always say the most important thing is to get 1 more dB than the others, okay? Essentially, that's all. So we work inside the building blocks. We are not putting PDKs together, but working inside the building blocks, or the designers of the building blocks. We are very good in these passive designs based in metamaterials, okay? Which is the activities or the projects in which we are involved now in the group. We have a project on far-field sensors, which essentially means that we are having very big gratings to radiate energy quite out of the chip, okay? And then be able to sense things that vibrometers or sensing even gases there, okay? That's almost finished. We have a very interesting project that is ongoing now, that is metaphor is we're using inverse design techniques to really exploit some wavelength structure at the very end. And we're quite getting very good results at this moment with this. So we are getting really devices which are very small, okay, and have really a fantastic performance in terms of losses. And we are using this kind of stuff for quantum, okay, with other people. We have contracts with a big company in quantum, okay. We are using this type of stuff. Also, we are going to work on this topic, which is what we call contactless chip fiber connection, which is a very simple modulus to focus from the chip directly without lenses to a fiber optics and to track the position of the fiber optics to get maximum performance. Okay, and we think that this kind of building block can be very useful, for example, for biosensing stuff in which you have to contact the fiber with optimum capabilities with a disposable chip. We also have a lot of work on filter design. We have brought from the fiber community design of fiber Bragg gratings to inside the chip, and we do really incredible designs. We can do a design with, I don't know, maybe 20 notches there and filter every one of them. And even we have been working a lot in this because silicon photonics, you know, gives quite some problems for big structures in the order of 1 millimeter. Okay, so we moved to quantum, to silicon nitride, and you can see there the difference between a silicon filter and the same filter in silicon nitride, and you see the difference is the same design structure, okay, but the structures are long and they suffer from the coherence of the phase, and silicon nitride, of course, is much, much better. And we are having a project with people in Canada to do this filtering for nanowires and for single photon sources. But really two projects that are very much related to the cátedra. What we want to do is to strengthen the ecosystem in Malaga are these two projects, which will be partially financed somehow by the cátedra, which is the multi-mode sensing scheme. I think Jonas already talked about that. Instead of using a single mode in a sensing stuff, we use several modes, and we will extract like geometry information of where things happen, okay? And also this other project, this is related to bioherent, and this one is related to AG photonics. We will be developing what is integrated photonics antennas for wireless optical transceiver, and specifically we will look at how to try to compensate, at least partially, not with a lot of elements, but you know, maybe reduced number of elements, so extracting some extra dBs from normal stuff from turbulent media, okay? Okay, just a few words about bioherent. Bioherent is one of the legs, okay? Was founded in 2022, it now has 15 people. Bullnet and Invierte put there 3 million euros, okay? And we are doing this machine and a cartridge to try to develop an in vitro diagnostic system for allergies, okay? So some of the, I don't know how to do this. Oh. I don't know if it's working or not. It was working. Okay, it's not working anymore. It doesn't matter. Okay, so what we are doing is we're targeting a high sensitivity, fast analysis, and high specificity tool, easy to use and low cost. Okay, and capable of opening a vast number of applications. We are targeting now allergy detection, but for this year we will try to do a more general equipment to collaborate with our people. Okay. So this is the cartridge, this is the system. It was a video, but it's not working, sorry. And, well, one of the things from the characteristics is from the photonics point of view, we have a multiplex of 7, very high signal-to-noise ratio, so limits of detection in the order of 1 to the -8. It's plug and play. The microfluidics has 2 independent channels there, and we have an exclusive, unreliable functionalization process, and we are working now in nanotechnology-assisted system for that. And the second company is AG Photonics. they will give a talk afterwards. Now, we have transferred to them some intellectual property concerning sub-wavelength waveguides, and also some techniques for optimally coupling chip to fiber optics. And of course, they will have our support on receivers, okay, and metamaterials. And well, probably the most important part there is integrated optical antennas. That was a work that was done by Pablo in his PhD, and now we are transferring it to industry, and we will try to do a product based on this. Well, last week we have the round A of Bullnet Capital, who entered with 2.7 million euros. So now I'm very famous at the University of Malaga because it's the first time that, single group is capable of bringing in total 6 million euros to the university from private funding. Well, you will know more about what AG Photonics wants to do, but essentially we will focus on free space optic transceivers, okay? And especially, the specific part where we think are strong will be scanning antennas, okay? Okay, so Malaga photonic ecosystem, is that what we want to strengthen, okay? And just a little bit about the numbers. If you look at December 2023, we were 9 professors, 15 researchers in photonics lab. There were already 15 people in biohearing, 4 people in AE photonics, so it's 38 people, which is not bad. It's all coming from the same group, okay? So it's well alienated, well coordinated, okay? Of course, not all the people in biohearing are photonics guys, but still they have the orientation, okay? And in a couple of years, we will be 66. We will be 66, all right? So it's quite a big number, okay? Well, this is the amount of money we have collected in the last 5 years, okay? So now we want to put there some technology. I still don't know how to do it, okay? Also, would like to do have some close to Malaga, some technology related to packaging, because we are good in, extracting light from the chip. I still don't know the tool to do that. That won't be done in the Cátedra Aperte chip. So the Cátedra Aperte chip is a collaboration between Innova, IRV, and University of Malaga. Everyone knows about this. It's a pity that Mario was not here, but you know that we will be the place where IMEC will put a second foundry in Europe, okay? And in this cátedra, there are 3 different sectors. The smallest one is silicon photonics. Silicon photonics is still a niche market, okay? So this leg is our leg. It's a small one. And then we have digital and analog. In analog, they're going to do RF and microwave type of transceivers, etc., or circuitry. And in digital, they're going to do VLSI for IoT, imaging, etc. So one of the important things that we are going to do there, as it was a requirement, it seems to be a requirement to sit there, IMEC, is to do a master in microelectronics and semiconductors, okay? Because almost 450 people will have to work there, so we have to start a training activity. So we have defined the master in microelectronics and semiconductors. There is only, I think, it's one subject there in photonics, okay? It has no sense to have a lot of knowledge there. In this is general master with VLSI design, but we will have an intensification in integrated photonics, very much related to our activity and to the activity of the 2 companies that we have founded. So this is the idea of the master, okay? So you see it's a microelectronics design master, but it has some photonics there, I don't know where, okay? Well, wherever, here. And also it has radio frequency stuff, okay? And the intensification in integrated photonics, you can see there all our expertise and all the requirements of the companies that we have founded, okay? So we know about all these things, design of integrated passives, etc. But also you see here optical phase arrays is very much oriented to give services to AG Photonics, biosensing, again, to give service to bioheat, okay? So this will be like very short courses, 3 days, like I think it was three credits, okay? We'll try to bring people there. We will, of course, are open to collaborate with all of you on this. And this is a little bit how it, the partnership. As you see there, we have only this small piece of the project, okay? And the two companies are very much related to what I call Malaga Photonics ecosystem, okay? Well, and that's all. Okay, and just for advertising, again, just trying to reinforce that photonics ecosystem in Malaga. And thank you to Professor Kamani, who was the one who called me to try to push this. We will be organizing the ECOC 2026 in Malaga, okay? So yes, please take that into your agenda, okay? You will be, if you remember, some of you have been in Optoel many years ago. It was fantastic. We spent a lot of money in good food, etc. We'll try to do the same. Let's see. Okay. So we will be organizing it, and the TCP is Robert and Ivana from Politécnica de Valencia. That will help also to strengthen the collaboration between Valencia and Malaga, which is important. And also, this is also quite important stuff. Okay, we have been selected as the permanent place where this Global Photonics Economic Forum is going to happen. Okay. This is, the idea is from Jose Pozo, from Optica. He would like to bring to Malaga every year the most important people, CEOs, etc., CTOs of big companies in photonics, okay? And they will do it every year in Malaga. First year is this year, 1 and 2 of October, and in 2026 it will joined with ECOC. So that will be a great week to strengthen the ecosystem in Malaga. And that's a little bit the stuff, sorry, because I think I spent 3 minutes more.
Thanks a lot, Inigo. Very impressive, and very happy to see how it's growing Malaga. Questions from the audience?
We are hiding. I know.
Hi, Inigo. Thank you very much for your nice presentation. I would like to ask you that. Sorry. I would like to ask you in the part of the sub-wavelength structures.
Yeah.
Okay, you said that you are very good in these structures and you have very fantastic results. And I would like to ask you about how do you maintain, in the technological point of view, the reproducibility of the fabrication of the structures, because normally in the sub-wavelength, the pitch are very, very small. Mm. And also I wanted to ask you in which TRL you are in these biosensors.
Well, biosensors are not using SWG, okay? I mean, we have some ideas on that, but actual biosensors are not working on that principle, okay? So concerning biosensing, there is the capability of having extra sensibility if you use sub-wavelength, but in fact, we have never used sub-wavelength in our biosensors, okay? So we have published theoretical papers. In fact, those papers have been referenced by big ones in the military sector in the United States, and they seem to have used it, good results, but it's not our expertise, okay? What we use in sub-wavelength, what we do in sub-wavelength, we have beautiful results, are very reproducible, is by E-beam technology, so it's in very low TRL, although there is people already, we have some of the gratings with sub-wavelength, we have been doing them with DBUB, okay? So, and we checked the reproducibility and it was good, okay? And now there are some people in France in the group of Carlos Alonso who is working on that, and also Alcyon Photonics, I think, is working on that. Okay, and they are doing sub-wavelength structures with with DUV technology. I don't yet know how much yield they have, okay? But for sure, I mean, if there is interest from the industry, in fact, we have some talks with TSMC, which seem to be interested in this, okay? Because as I mentioned to you, you really can get building blocks which are very, very small and with very low losses, okay? We are working to get milli-dB type of couplers for quantum applications, okay? Probably we won't measure that, okay? But still there is the root there. So I don't know, let's see how it works. This is still research, so.
Thank you. There was another question?
Thank you very much for your interesting talk. I was wondering which are the main foundries you work with, if it's not a secret, and if you could compare the performance of your light adapting structure for chip to fiber compared with a typical grating coupler, let's say?
Okay, the one I showed you before, that is, which is the prism-assisted coupler, that is world record in terms of efficiency and bandwidth. It has, I don't remember now the numbers, okay, but it was like, I don't know, maybe 100 nanometers and 0.something dBs of losses, okay. We have shown that experimentally, and in fact, we tried to set an internal project with Tingle to move that. And this is one of the topics that is in the business plan, let's say, of AG Photonics. So, well, those couplers are really impressive. The problem is that you have to really increase the TRL, okay? And for that you need money, you need the partner, because we don't have packaging stuff, but maybe with Guillermo, he will be having very nice machines there, we will be able to do something, okay?
And regarding the foundries, or is that a secret?
Well, no, I don't think it's a secret. Bioherent is all the stuff is being done yet in pilot lines, research stuff. We are working with Cornerstone, which is very low price. Okay, I don't know if they are friends of us or what happened, but it has good prices for us. And now AG Photonics, I don't remember exactly, but I think this AMF, what they are looking at, okay, which has very good processes and also good price.
Okay, thank you very much.
Okay.
Okay, any other question? So if not, let's thank again Inigo. Our next speaker will be Ignacio Esquivias. He's coming from the Universidad Politécnica de Madrid, and he's going to present his initiative on this PERTE Cátedras.
Hello, good morning. Thank you for inviting me, Pascual. And now I'm going to present the pretended activities of our industrial chair between UPM, Universidad Politécnica de Madrid, and Indra. And we have we are a bit different than previous chair that I have seen today, in the sense that we have a single company, not several companies. Indra, we will explain a little bit. And the university has taken this as some institutional, so we are quite different number of groups in the university with different field within semiconductor and microelectronics. Part of that is in photonics, then I will explain with some more detail. Okay. So probably you all know what is Indra. Indra is a very large Spanish company, which is now in many countries and is considered multinational. And the core of the company is rather defense technology. They are fabricating complete systems for a lot of defense applications, also civil applications, especially in transport, in airports and and planes. And also they have also a part that is consultancy services for software for external companies. And for that activity, they consider microelectronics something very important for them in all the complete set of activity. And then they were interested in having this industrial chair with the UPM, because UPM and Indra haven't had a lot of common projects for 20 or 30 years, especially in the area of microwave antennas and radio frequency. And then some figures of the company is almost 4,000 million revenues annually, and they have more than 56,000 employees. They have presence in 46 countries in the world, and they have commercial operation almost all around the world. In the case of the Universidad Politécnica of Madrid, you probably know that it's the largest technical university in Spain. We have 18 engineering schools, 36,000 students, more than 200 degrees on bachelor and master, and also 18 of them are related to electronics or microelectronics. We have a very long tradition in semiconductor technology. As early as in 1969, Antonio Luque founded the so-called semiconductor lab with a complete clean room with fabrication technology from all the standard fabrication for silicon technology, from epitaxy, oxidation, diffusion, photolithography, chemical etching, metallization, even dicing and bonding. In 1974, they developed the first Spanish integrated circuit with 4 transistors, not too many, but more than 1 transistor. And in 1975, the first Spanish solar cells. And this photo brings back to me many memories, because I did my PhD growing polysilicon solar cells in this clean room. Now and then in the Polytechnical, we have joined researchers from 3 different schools. My school, that is the Telecom Engineering School, from the Industrial Engineering School in the center of Madrid, and also from the school in Telecom System in the south of Madrid. The researcher belongs to 6 different research institutes of center, the Center of Industrial Electronics, and 4th center in my school, the Center of Advanced Materials and Devices for Information and Communication Technologies, the Institute of Solar Energy, the Information Processing and Telecommunication Center, and the Institute of Optoelectronic System Microelectronics. It is considered officially as a singular infrastructure for the clean room facilities, and also the Center of Research in Software Technologies and Multimedia Systems for Sustainability in the south of Madrid. Then we include all the steps in microelectronics and all fields in microelectronics, from fabrication with 3 different clean rooms, with all, especially for silicon, 3-5 materials, and also other more advanced materials. We have different systems of growth, MBE, MOCVD, and we have what I think is the only lab with capability of growing silicon bulk, silicon wafer by Czeroklasky technique. And then we can fabricate a lot of different devices, from transistors to solar cells to lasers. This is in the field of fabrication. In the field of design, we have groups which have specialized in ASIC and FPGAs, also groups in high frequency, in millimetric microwave integrated circuit, also in photonic integrated circuit, reaching microsystem by combining different chips, and also have an important 2-3 groups working in open hardware architecture, what is called RISC-V, and in the complete system by doing the own ASIC design and then the complete system. In the case of the Indra UPM church, The main objective is to consolidate and structure for the promotion of research, training, dissemination, and public-private collaboration in microelectronics, so close collaboration between UPM and Indra, expanding the offering in education with the fraction in research and development to transfer the results to the productive sector, to the company, and to increase the number of qualified people working in microelectronics in general. We will have 4 different research areas. One is related to the design and testing of open architecture microprocessor, that is RISC-V. The second one is devoted to design and testing of photonic integrated circuit. The third one is design and testing of high frequency and mixed signal ASIC for heterointegration. And 5 is the fabrication of wide bandgap semiconductor device based on gallium nitride and narrow bandgap for semiconductor device for indium gallium arsenide or for electronic device for high speed. The work is divided in work packages. We have 4 technical work packages with the 4 fields I have explained, and also the classical management work package for education and training, and now one for impact. The chair is led by the Vice Chancellor of Research, but the practical leader will be Professor Maria Luisa López Vallejo, and I will lead the part on photonics. In the field of photonics, our general objective is to explore application of integrated photonics in commercial systems developed by Indra, at least trying to reach TRL5, a medium level of TRL, and we want to specialize in fabricate photonic integrated circuits for microwave beamforming, and also to explore some other emerging applications of photonics and optical technologies which were in the interest of the company, as metamaterial for immiscibility, optical transceiver, photonic ADCs, and co-packaging of photonics and microelectronics. Regarding training, we plan to include all levels, so from massive open online courses to using especially micro-credential. I will explain with some more detail this micro-credential. We also increase the microelectronics courses in the official UPM master degrees. We plan to fund several bachelor theses and master theses related to the research, industrial doctorate, and also postdoc position. These micro-credentials are very short courses. They are especially for continuous education, so for people which is already working, not for people, not for new students. It can be for specialization and requalification, also generalization. It can be done in company or the university, and most of them will be experimental. And this micro-credential will be grouped in joining 2 types of degrees: expert, which is between 15 and 30 HCTS, and joining 2 experts, we will have a UPM master degree, which we call in Spanish título propio, not an official title. For instance, this is the 5 experts that we have planned. One of them is in photonic technology under integration, with that is the micro-credential, and this set of micro-credential can be done separately or of all of them, providing them the complete degree. And some number will be that we will have not 4 years, but 3.5 or 3 years, if we were lucky. And we are including 6 UPM research centers, 3 engineering schools. We presented in the project the curricula of 24 senior researchers, but in total we are involved in the different research centers more than 200 researchers. We prepare 31 micro-credentials that will make 105 credits, and we plan 60 bachelor or master theses, 11 industrial doctorate, and 3 postdoc. And you can contact me for if you want more information, and after everyone, we are hiring. That's everyone. Yeah. Okay.
Thanks a lot, Ignacio. Questions from the audience?
Yes, thanks, Ignacio, for the nice presentation. I like very much the micro-credentials approach that you propose. Can you explain it a little bit more, please?
Yes, this is something that is official.
Microphone.
Oh, excuse me. It's official at the European Union level. They are preparing different certification processes, and it is something that you propose something between 3. I think the maximum is 8. Yes. We propose here 3 or 6, but you can choose. And it is the main difference with the normal course is this 35, that you have the complete guarantee procedure, then you have a guarantee system that is 35, and you get a certificate that is official, and then you can send to your employer everywhere in Europe. That is the difference. And it is rather for people who is already working, so as continuous education. It can also be offered to the student of a normal course, or the master or grade, if they want. But it's rather, our plan is rather to set it at the end of the evening or in the weekends, so rather for people who is already working than for young students.
Thank you. Any other question? Okay, if not, let's thank again Ignacio.
Thank you.
Thank you. So next speaker will be Stefano Signorini, and he's going to show the industrial chair combined from Universitat Politècnica de Catalunya and ICFO. So the floor is yours.
Thanks a lot for having us here. I work in the group of Valerio Pruneri and a postdoc there, and I'm going to give you an idea of what it is the framework, what is the program, the ideas within the program of the Cattedra per the Chip between Universitat Politècnica de Catalunya and ICFO. And the basic idea is that the topic of the Cattedra is going to be chips for advanced architectures and photonic systems. So the idea is that we have activities related to semiconductors, so development of hardwares for microelectronics and also for photonics. And in this sense, the main goals of this Cattedra, of this program, is to attract the pre-university talents, but also to develop an educational network related to these topics, and at the same time promoting female vocation and participation. And to do so, we think that it's fundamental to develop an ecosystem where we have research centers and companies. And in particular, in this case, we're going to develop PhD and research activities with 13 companies of the ecosystems, and also 2 research centers. And the budget, it is 3.7 million from the public and 1 million from the companies. And the Universitat Politècnica de Catalunya is going to give the framework for the development of this ecosystem, both on, let's say, on the academic side, so the formation side, but also to provide the opportunities for interaction between the companies and the research centers. And in this sense, the Universitat is going to give, of course, pre-university studies and bachelor professional formation, of course, in this sense, but at the same time is going to provide activities for master, PhD research activities, and they will foster within their network the formation of interactions between the companies and the research activities. In this sense, so with this topic of the advanced photonics and electronics, we have the 2 research centers that are Barcelona Supercomputing Center and ICFO. With the Barcelona Supercomputing Center, there are already some companies, well-known companies, that will participate into the program with their activities, mainly related to electronics, microelectronics, okay, for advanced computation. Then there is the UPC, of course, that is going to give formation, but also they have an ecosystem of companies that will help with the electronics and also photonics activities, so for joint activities with research and industry. And then there is ICFO, that I represent here today. And we are going to work together with the spin-offs that we have already launched, like QSide, that maybe you saw the talk yesterday given by Carlos Avellan about QSide, but also Lux Quanta and Curve, that are all spin-offs related to quantum chips that came from ICFO. In particular, as ICFO, we focus within the program, with the framework of the program, we focus on quantum integrated photonics. So from now on, I will give you an idea of what is the, let's say, what to do, what can we do, what we are going to do, and what we are doing within ICFO in the sense of integrated photonics, but for quantum, mainly for quantum activities. So first of all, pick for quantum, but why? Maybe you all know maybe this experiment from some years ago in the group of Zhang Weipan in China, where they demonstrated for the first time the quantum advantage with photons. But what is clear is that, okay, it's an amazing result, but it is really bulky. So it is resource demanding, it is huge, you need a lot of students to do that. So it's not scalable, so that's the main problem. And what we think is that through photonics, integrated photonics, we can scale up, so develop large-scale quantum networks and quantum applications and devices. So that's the idea we have also in ICFO. So we think that we have to start from the quantum properties of light, in this case, for example, and in order to enable them for applications, we think that integrated photonics is like the enabling technology for that. So you start from the quantum properties, you go into photonics, integrated photonics, and you can develop your application and bring that to the world, let's say. And in this sense, for example, is what we have done with QSide and Lux Quanta. So you start from a practical problem, from a question that is like information security, for example. Then you develop your technology, your science. Then you go into technology, let's say, with your prototypes. In this case, are integrated photonics prototypes. And then we arrive at the spin-off that is QSide and Lux Quanta. QSide, as you know, it is related to quantum random number generation, while Lux Quanta is more on continuous variable quantum key distribution. So in this sense, internally in ICFO, we have like a value chain, if you want, where we start from our science and technology. ICFO is a huge research center, so we have many, many topics that we are working on related to photonic sciences. So we start from our knowledge about chip design or 2D materials, graphene, and so on. Then we move towards vertical, so like applications. So we define it in sensing or imaging, transceivers, whatever. And once the application, the product, the idea of the product is quite clear, we try to develop the product or the company. So then we spin out, let's say, the activities. And this is because actually internally we have several technologies that we can leverage, like from peaks for quantum, but also classical applications. Then there are like SPAD images, or single photon cameras, single photon devices. We also develop quantum dots that can be coupled to photonic integrated circuits and other materials like 2D materials, graphene, and also atoms. All this is like within the framework of ICFO, and that we want to use to work towards application in quantum integrated photonics. In this sense, internally, we also do infrastructures for the development of these prototypes. So starting from simulation and design, interconnection of both optical and electric interconnections. We can work with functionalization, characterization, also the integration in packaging. So these are like capabilities that we have internally. And putting them all together in the proper way, we then develop the final device that in our case is a quantum photonic integrated circuit for different applications. In this sense, we already worked with different materials. So you know that in photonics now, the material platform is one of the biggest hot topic, let's say. It has always been a hot topic, but now it's getting more and more important, let's say, to find the right material. And as you know, depending on the application, you have the material, or maybe you don't even have the material, so you have to find also hybrid solution. Internally, we already work with several materials like indium phosphide and silicon on insulator, and now we are developing also designing new chips based on silicon nitride, IOX, and also hybrid materials and so on, and lithium niobate as well. So now I'm going to give you just very quickly an idea of the technical activities that we are carrying on in our group, in ICFO, together within this program, let's say, they can fit well. And we are working on satellite QKD, with continuous variable QKD, always on chip. And also we are developing processors, so related to quantum computation, classical computation on chip, of course. We are developing sources for quantum sources on chip. And also we have a project on quantum sensing on integrated photonics. So within the framework of EuroQCI, there is a why. So how do we develop a large-scale quantum-safe network and the internet? And yeah, within the project EuroQCI, the idea is to couple together, let's say, ground communication and satellite communication. So it is clear that we need trusted nodes in satellites. And so, I will not go technical into this, but the basic idea is that if we need satellites, we need transmitters, okay, quantum transmitters on the satellite. And to have a quantum transmitter on a satellite is very useful to have a peak because of the payloads of the satellite. So if you want to go small, you want to go and with low energy consumption, want to be efficient, developing a transmitter on chip can be really a turning point for satellite quantum communication. And so we are working on that. Also within activities and projects like Quango and QDICE. And internally, we already developed several transmitters based on for QKD, and mainly in fiber. And now we are, let's say, translating everything into chip in order to enable this transition for satellite communication. Another activity is related to continuous variable QKD. That is, of course, related also to our spin-offs like Quanta. And when you work with quantum QKD, continuous variable in this case, you want the why is that you want quantum communication safety, also based on development of quantum computing algorithms. So basically you have a transmitter that is Alice and a receiver that is Bob. And what you have on the transmitter is always, a light source, not like this one. So a light source, an amplitude and phase modulator, so like IQ modulators, and then you need a power controller and so on. What we have done within Civic is to integrate on the same chip the IQ modulator, so the amplitude and phase, and the power management, let's say, within the same indium phosphide chip. And so this is what we have done experimentally. Also, it is already demonstrated. And of course, we put together several elements on the same chip, working at gigahertz, well, almost gigahertz, I would say, in that case. But in this case, we demonstrated a secret key rate that is like 0.4 megabits per second. And we demonstrated, of course, we demonstrated this, the working principle, of course, with this chip in indium phosphide. Of course, the next step is going to increase the integration. So this is not enough. You have to integrate also the detectors. You want to integrate the laser source. You want to integrate also the packaging, the optical packaging, which is one of the most important problems, as we saw in this conference. The next activity is related to processing. So we are working at the moment with classical processing, but also it's going to be also quantum. The basic idea is the why here is that with the scaling up of the computation, power requirements related to AI and all the applications nowadays, of course, data centers are going to explode in terms of energy. So the idea is moving to photonics instead of electronics in order to reduce the energy requirement. And photonics can be, of course, the good solution in this sense. And the basic idea is that you develop a system that is a cascaded matrix of Mach tenders, okay? That have to be reconfigurable fast. So then there's always the thing that we have to go very fast, so gigahertz and so on. Here, what we've done is to start with a prototype. It's a 2x2 matrix, able to perform matrix vector multiplications. But of course, the applications are related to simulation, optimization algorithms, and so on. And what we've done now is we have on chip, we integrated the electronics, we integrated the optics. We are performing experiment on this and controlling directly, from a computer the reconfigurability of our chip. So we have electro-optic interaction in this case. And what we are targeting now is to move to other platforms in order to increase the speed. So here we're working with silicon, but what we are studying now is to translate this to thin film lithium niobate in order to move to faster computation. And also silicon nitride is something that we are considering for quantum, because if you take this architecture, photonic architecture, and you power it with a quantum source of light, actually you are moving into quantum photonic processor. So that's quite not straightforward, the translation, but the starting point is the same, let's say. Of course, another activity is related to peak-based quantum sources, because when you have an application in quantum, typically you need a source of light. Can be single photons, can be photon pairs, can be entangled states. So typically, what you need is to be able to engineer your source depending on the application. So we do this internally for quantum integrated photonics, and it can be application in quantum sensing, communication, or simulation. And we engineer our own source. This is based typically on nonlinear optics, so we generate photon pairs, and based on Chi2 or Chi3. And an example of this activity is a project that is related to on-chip undetected photon for mid-IR sensing, in which we are engineering our entangled photon source in order to have photons in the mid-IR and the infrared, as I will show you now. So the basic idea of this project, the why, again, is we want to develop an on-chip mid-IR spectroscopy and sensing device, okay, for gas sensing in this case. And in order to translate from the use of, to detect things in the mid-IR is always a problem. The instruments are super expensive, bulky, they need cryogenic temperatures and so on. And we want to translate this to chip through this quantum technology that is undetected photon measurements. And the basic idea of undetected photon is that you need two cascaded sources. So these are two photon pair sources, A and B. You cascade them in a way that the two are overlapped, the emitted photons. In this way, the two sources are indistinguishable. So what happens is that if you go at the end of the emission, so at the end of two arrows, red and blue, and you perform a detection, you don't know if the photon comes from the first source or from the second one, because the two sources are never emitting together. This indistinguishability, this lack of information, gives rise to quantum interference. If you put a sample between the two nonlinear processes, the two nonlinear crystals, what happens is that your quantum interference will take also the signature of the sample. So in other terms, if you measure the interference pattern, okay, as you see in the plot, when you put a sample, your interference pattern will shift due to the phase sensing, let's say, of your sample. What is really interesting here is that you can engineer your source in a way that the red photon, let's say, is in the mid-IR, while the blue photon is, for example, in the infrared or in the visible even. And due to the entanglement between the two photons, the information about the sample that is probed only by the mid-IR photon can be detected by measuring only the infrared photon, okay? So we can, in this way, get information about the mid-IR sample, but we don't need technology in the mid-IR to detect it. And the idea is that we already developed this on chip. That is the first time that has been done on chip. It has been demonstrated free space and everything, but never on chip. We demonstrated this in silicon. And what we have shown is that actually you can perform phase sensing at 2 microns to start, let's say. Then you can move further in the mid-IR. At 2 microns using an on-chip undetected photon system. So to conclude, within the context of the Cattedra PERTE chip between UPC and ICFO, we want to attract pre-graduate talents. We want to foster the education in the field of sensors, field of semiconductors for microelectronics and photonics, but at the same time to develop an ecosystem between industries and academic entities in order to develop advanced research in applied quantum photonics and also microelectronics. And the topics that we are going to touch, let's say, that we are working on within this context are related to quantum integrated photonics, related to the topics that I showed you before in this short presentation. So thanks. If you have a question, I'm here.
Questions?
Thank you very much. Really insightful talk. Regarding with quantum sensing and this mid-IR sensing, you mentioned there over 2 microns wavelength. Can you control the emission wavelength?
Yes. This is for a mixing process. So the thing is that if you move your pump wavelength, in our case, we are pumping at telecom C-band, so 1550. The nice thing here is that we engineer the source in a way that you can move like just by 5 nanometers, and you are moving your mid-IR photon like more than 40 nanometers. So you can like perform a spectrum of in the mid-IR if you want, yes.
But can you reach up to 3.3 microns or?
Yes, if you engineer properly the source, yes. That's the idea, actually, yeah.
Okay, thank you very much.
Any other question? So I have a simple question. How do you plan to align all this research? Because I mean, you show like the whole quantum applications or research lines from ICFO.
Yeah.
Would you be able to align all this with the PERTE?
Oh, yeah. The idea of the PERTE is within the PERTE, and I mean, related to ICFO and UPC, there are going to be two PhDs and a technical position. And the two PhDs will work mainly on the topics of the, this position will be related to the spin-offs that we've already launched. The point is that these spin-offs are mainly related to imaging and also to quantum communication and QRNG. So to align them, let's say that all this stuff that I showed, maybe in a way touch all these activities. So for example, the CV QKD or the satellite QKD are actually related to our activities in the group and also to the activities of the spin-offs. So there is like a good match in this sense. The other two activities, yeah, as you said, there are many things, but maybe I'm not going to go exactly into that, but they can, like this one, for example, the sensing, can provide the basis for the development of other, or for the, for the development of devices, for example, for the PERTE in this case. So maybe it's not going to be everything to the PERTE, but since everything is based on peaks and quantum peaks, for sure, all the activities can, in a way, be beneficial for the PERTE activities. I don't know if I replied to your question, but I'm not Valerio, so Valerio would be better on that.
Thank you very much. So if there are no more questions, please, let's thank again the speaker. And last but not least, before the coffee, because I know you are willing to go for a nice coffee, we have our host today here presenting the Cátedra of UPV. It's called PIC UPV. And we have Pascual Muñoz and José Capmany, both from university. Please, the floor is yours. I don't know how you're going to do it. I'm really willing to.
Thank you, David. Thanks for the introduction. Thanks, everyone, for attending. So José and I put together this program last weeks of August. It was pretty interesting times there. So we're going to present the photonic chip cátedra. But first, I'd like to give a little bit of context. So this is in the context of a whole supply chain in Spain for photonic integration that has a technology segment and an application segment, as you can see in the image with yellow and red. So it spans from research through foundries and then design, test, and packaging. And it also has fabless companies, equipment suppliers, and end users. And this supply chain is rather well scattered all around the geography of Spain, as you can see in this picture. So it's at least present in 8 of the autonomous communities in our country. Not all the links of the supply chain everywhere, but it is rather well represented. The top economies in Spain are present in this supply chain. So PERTE is being mentioned all times, all around. It was the introductory talk of this year event. It is summarized here in a snapshot, and I just wanted to bring attention and to put into context that the Cátedra chip that we are discussing today is just this tiny part of education that they devise, as it has been mentioned several times, to create the human labor and the skills that are needed to do all the other things which have a significant number of zeros more behind than the education thing. So this is the context. What are we doing or what are we planning for the Cátedra PIC UPV? So it is who is participating. It is, of course, us from 2 internal units or groups, UPV Fab and Photonics Research Labs. And we were successful in convincing 5 companies, Spark Foundry, the 3.5 Foundry starting in Vigo, BLC Photonics, which is our spin-off, well, now part of the group Hitachi, and then Ipronics, Omatedia, and CalSense. So as you see, we are somehow encompassing technologies, but also end users with applications. So in that sense, we oriented the topics towards their industrial interest. So Spark was interested in starting research on aluminum nitride technology. VLC Photonics want to explore the capabilities of 3D nano imprint for packaging and test. And then in the more vertical side, we have Ipronics with programmable photonic processors, Omatedia that is interested in coherent LiDAR MIMO. And last but not least, our third spin-off from the group, CalSense, which is interested in structural sensing, instrumentation for structural sensing. So these are the industrial participants together with us, and accordingly we designed a training program, okay? So our training program includes specialization master. As all the others, we are not pursuing an official degree, so it's gonna be a UPV degree on photonic integration that has mainly two parts. So the part, let's say the courses, where you find two courses with 4.5 CTS, which address the transversal knowledge on design, fabrication, and test of the photonic integrated circuits. And then we have 3 courses which are application specific, so oriented to programmable photonics, to LiDAR, and as well to sensing. So we plan to open 10 positions per year. Ideally, this would turn more or less into 2 positions per topic of interest for the companies to do a second part of the training program, which is an industrial master thesis. That means it's going to be with tight interaction with the companies. You will see later also companies will participate in the left part of the slide, so in the training courses. But then their main role is going to be probably, supervising in the companies the activities of these master students to pursue their master thesis degree. This is the training part. There is, of course, in this technology field, there is, of course, a research part, because we're creating new technologies. And then what we have planned is, aligned with the 5 industrial sponsors, 5 postdoctoral positions and 10 PhD positions for the 4 years. So last slide were 10 positions per year. This is going to be 15 positions, so 1 + 2 for every line for the 4 years or 3 years or whatever is left, since we got the resolution yesterday, 1/26. So good thing of these industrial chairs, we believe, is we have the opportunity to do all this training in a, let's say, less academic way. And that means that we can do this in our facilities. So what we bring to this training and research program is, of course, our facilities in the clean room, UPV Fab, where we have all these equipment ready and some process already running for the different parts of the different areas of activity in the clean room. And then we have allocated some budget as well to co-fund some equipment required for the research in the particular case of manufacturing, so etching of 3.5 semiconductors as well as 3D nano imprint. And then I will give floor to Jose. He can take it from here.
Okay, thank you. So actually the second part of the cátedra is the second institution or group inside the proposal is the UP PRL Labs. So here we have an infrastructure. I think you had the chance of visiting yesterday UPV Fab. Our lab, our research lab, is a little bit like complementary. It's equipped with all kinds of setups and instruments that you will need to test your chips in, let's say, a more kind of systems experiment environment. And then, of course, will also be open to our students. The lab is very well equipped. I have to say, although some things still will be renovated and some new equipment probably will be acquired. As it stands today, it's fine for taking care of the students that we will support within our cathedra. So, of course, it's not only about material resources, also about human resources, and of course, more principally human resources than anything. So, the team is quite complete. It brings, of course, academics from the group, and researchers, postdocs, and also it brings leaders and CTOs from the involved companies. So you can find here the list of the people who will be involved in the academic activities and in the training activities. Pascual mentioned before briefly some of the contents of the cathedra, which are our objectives. But further than that, we would also like to comment on the impact. Impact is very important. We are doing this to have an impact. And our impact, the most important goal is to train people here for the cathedra. And this is our principal goal. So, of course, in order to have a roadmap for these goals, we need to define, or we need to have some KPIs. The most important ones are those related to training. Of course, like with any other proposal, you are asked for scientific and technical KPIs, which I will not go very far today. I want to concentrate on the training KPIs, which are for us, in this particular context and in this particular project, the important objectives. So I want to draw your attention to a couple of important KPIs beyond the number of students that Pascual has already mentioned, PhDs and postdocs. Our program is designed in such a way that, as Pascual said, there will be an MS course in-house. Okay, so it will be organized by us, and he's been through the technical description of the main subjects. But this has to be complemented with other activities, and I want to highlight, of course, the fact that we want to train our students in business skills. We want to give them soft skills related to business, because at the end of the day, the profile of the students, I mean, we are training them for various different outcome jobs. We are thinking not only about them joining our spin-offs, which is, of course, it's a very nice thing, but also to provide them with the skills to set up their own companies, if applicable. So there is an important part on training on business, but there's also another important part on allowing them, providing them the opportunities to attend internationally renowned and design schools. And of course, in the context of Europe, you can think about silicon nitride, and indium phosphide as technologies. So this is also contemplated as well in the program. And finally, last but not least, the possibility probably of some of them joining or complementing their studies, this time with an official master course that will be, we are working on that. It's a master on quantum information and photonics, which will be launched in 2025. So it's already internally approved in the university, so it will be launched after accreditation, if that happens. So that's the most important things I wanted to highlight. And just to summarize, this is a quite dense view graph, but just to summarize, I want to conclude with the fact that this cátedra gives us the opportunity to train people, interact with the needs of our supporting companies, trying to have this bi-directional flow from the company to the academics. This is going to be very active, not only because there will be students coming and going from the companies, but also because we want to provide with the opportunity of having industrial doctorates, which is a very, very valuable figure in the companies. And we want to leverage on this unique opportunity that the PERTE has given to us. And basically, well, look, we're looking forward, and we are looking forward to receive the applications of students as soon as we can open this program. So from my side, that's all. Thank you very much and for your attention.
Thanks a lot. Any question to Jose or Pascual? I haven't prepared any question for you.
You should.
Yeah, I know. Not really?
Okay.
Come on. I know in detail the program.
Yeah, you can ask by the coffee break, so no problem.
Yeah. So I think it's best. So thanks a lot. This is the end of the first session. So the coffee is ready for all you. Thanks.
Thank you.
Als ik moet verder gaan?
Ja, die.
Ja, dat is goed. I'm a bit surprised by the number of slides, actually.
It's the only presentation I saw on.
Yeah, sure. But we tried it before. What's wrong? No, nothing. I'm just wondering which version of Glow. Can you just check the last slide?
The last one?
Yeah, maybe not showing it on screen. I'm not sure.
Yes, we can do it this way.
Okay, thanks.
Yeah.
Check it. I hope it's. No, it's fine. It's good. So good.
All good?
No, good. Yeah, sorry for the panic.
No. All fine. So, go ahead.
Thanks.
Welcome back, everyone. We've arrived at the final session of this Photonic Integration Week, and it's an honor to introduce to you Gregory Pandreau. He will be talking about Omatida LiDAR.
Yes, thanks. Yeah, thanks a lot. Thanks first of all to Pasquale for inviting me giving the talk today. So you might know my colleague, the other co-founder of Omatida LiDAR. You might never seen me before. I think or at least online. That could be the way you have met me before. So I'm also the co-founder of Omatida LiDAR. And I was asked actually by Pasquale, because we work on a project together, to talk specifically about in-cabin. Now, I also checked the program. I realized I need to talk for 30 minutes. And talking 30 minutes about in-cabin, it's challenging, right? So I'll try to keep in-cabin in the back of my mind, so that you will see along the presentation, the in-cabin comes back from time to time. But it will not be the main focus of my talk. So first of all, Omatida LiDAR, I think you have seen us already appearing in many presentations. Pasquale being the latest presentation where we have 2 PhDs around LiDAR. So we were founded in 2020. So Eduardo, myself, Jose created the company in 2020. We have now 21 employees. So this is the number needs to be updated. So and we stretch between 2 countries. So we stretch between Spain and the Netherlands. So why the Netherlands? So I've been working at the university in Delft for 15 years, I think, something like that. So it was very difficult for me to move to Spain. However, what we do, we also benefit from because I know it was discussed here extensively about having access to people, right? Now we use actually both entities to actually attract talents. So just to give you an example, so here we talk mostly about peak photonics, which is nice. I mean, in Holland there is also a strong photonic industry. However, what we see now is on the electronic side. So, and what we see actually, it's easier to find people in Holland with a proper background to design a ASIC than in Spain. So actually, the team is now growing on that side. So we are now five since yesterday. We are 5. And in Spain, we are then 15. Right? So that's roughly the split between the two companies. By the way, also our business unit will be also based in Holland for proximity to market like Germany and let's say East, right? East Europe. So at the core of the technology, we have a peak, right? And I hope that's why we are here today. That's very important. And we have gained visibility across the 4 years. We have gained visibilities across different markets, mostly thanks to the product that we put on the market. So that was one of the key, when we started, is to be able to be on the market and have a product as soon as possible and sell this product. And we have been selling it then in different, one of the free market presented there. So we started from space. We were supported by ESA at the time, but then we slowly moved to industrial metrology and civil engineering. So what we do here is actually the system is mounted on a scanner. So we mount it on a tripod. So market competitors are typically laser scanners, so Leica and the others, Nikon. So we mount it on a tripod, actually we scan, right? So we're able to produce a line of points, and we bring this line of points through the scene, or through the object to scan, and we're able to produce then a 3D-point cloud. Now, so in cabin, I didn't forget in cabin. so what is in cabins? So there is this tendency to look outside the car, of course, with the LiDAR for the autonomous driving. So being able to have no driver, like Waymo type in San Francisco, no driver in the car. However, there is also this tendency to look inside the car. Now, I had a discussion yesterday on this. So I'm not a policymaker, but so here I'm just presenting a solution. So there's also a need apparently to look at the passenger itself, so in the car. And two main needs. One is actually the occupants detection and classification. So the classification is important. So it's not only a question of being able to know who is inside the car, but it's also who is inside the car. So is it a woman? Is it a man? Is it a child? And why is it so? Is because there are competitive technology like cameras and radar, but radar has very limited number of points. So it will be possible to know if someone is sitting on a seat, but the radar will never give the information on the person. So then they have to couple it with, usually what they do is they use a weight sensor, so then they know if it's someone heavy or not. So then they will be able to tell if it's let's say a man above 100 kilo or a child, that they will be able to say that, but they will not be able to go beyond that, right? So there's still some limit there. And now the need, because to come back to the discussion yesterday, why people want this is because there have been some accidents in the US, for example, where a child were left at the back of a car for a day and actually they died. So still there is some needs apparently for this kind of sensors. Now, if you go a bit beyond, this is where we would like to step in. Beyond that, there is also the driver, right? Being able to monitor the driver, especially for looking at vital signs. So being able to see if the driver is still able to drive the car. So if he's not having a heart attack while driving. And drowsiness, right? Drowsiness, so far, the way it's measured is actually, they are just following the body motion, right? And if the guy starts falling, his head against the wheel, there is some red flag, right? To say, oh, there is probably something dangerous there. So far, cameras, radar used. I mentioned the application of radar with limited information. Cameras are becoming to be disregarded also for autonomous driving because they carry too much information. So the camera can scan your face, so it's nice for facial recognition, but it's too many information, right? Because facial recognition will bring you to your social security number, etc., right? So normally cameras, and it's not my information, by the way, I take this from Innoviz. Innoviz is also a LiDAR provider on the market that have seen a decrease in use of cameras because of privacy reasons. However, LiDAR also been considered. So if you go to Infineon, so Infineon has a time-of-flight LiDAR. They also they are actually selling it to put it inside the car. But time-of-flight, based actually on our partner on the project, they also tend to have some limits. And actually range accuracy is actually a limiting factor, especially for, and I will come back to this later, especially for vital signs extraction. Now, so how did we end up doing in-cabin LiDAR? So there was a call last year in September for a Korean-Spain strategic program, so KSSP, and of course, yeah, it was. There was not too many Spanish companies that could apply. I think we were 3 in a call. 2 were selected because it was difficult to provide the Korean counterpart. Right? So we had a chance that we were already involved in a program with a Korean company called Dongwon. And what we did then, we wrote the project in such a way that we will be looking at longer range LiDAR with our Korean partner, with the help of Pasquale and his team. So meaning, so long range, so in this case, Pasquale will provide the laser, or at least the amplification stage required to go to 300 meters. While with IDNEO, we said, okay, fine, we can also look at the other side. So instead of looking outside, we can also look inside the car. And then try to use not time-of-flight-based LiDAR, but actually our solution. So then what do we do differently, right? So we don't do time-of-flight, right? So time-of-flight is the dominating LiDAR providing system. So time-of-flight, I'm not going to give a course on time-of-flight here, but time-of-flight has some limitations, and some of them will be explained later on. But it's now well admitted that time-of-flight will not be used or considered anymore for mobility applications. So what I mean by mobility, it's not only the car driving alone, but it's also robotic, right? I think we had a discussion on this yesterday also on robotic. And to put a market perspective onto this, so we are not the only one doing FMCW LiDAR, which is nice. And to put two competitors, not competitors, they are friends-ish, on the market. So I put here Silk, so they are both Californian-based company, but however, they provide single-channel system. So single channel is still 1 point scanning the scene, right? So one is actually Silk. Now, the nice thing about it is that 20 years ago, I used to work in a company in England called Bookham Technology, and the CEO of Silk was actually my boss at the time. So it's a very small world, right? We end up, so we used to work 20 years ago together, and now we end up doing LiDAR together in the same field. And AEVA, so AEVA is very interesting. So if you have followed the news, there was an American lander last week landing on the moon. Now all the system, the sensor system fell down. So they were not able to see the moon. They were not able to see where they were landing. However, they embarked on board a prototype from AEVA and NASA. So it's a one-channel FMCW LiDAR, so they had to switch to the FMC LiDAR, and they managed to land thanks to FMCW LiDAR. Right? It's very important, right? So it's key. Huh? So thanks to AEVA and NASA, the lander was able to land on the moon, right? So that means there is a need for FMCW LiDAR, right? Beyond automotive and beyond in-cabin, right? Just to keep track on the main program. So what is the implementation here? So here I will detail the single channel concept. That's the one that's used by our competitor Silk and AEVA. So the nice thing with this is, so standard time-of-flight, LiDAR is simple. It's a laser source and receiver. So standard time-of-flight system, they said, okay, fantastic. Why don't we use the CMOS camera, so the one on your phone, and we collect the information back from a pulse of light that is sent to a scene. So this is fantastic. However, the electronic can just capture the intensity, right? So the electronic will give you a readout. That's very nice, but that's the only thing they can do, right? So what we do here, we pre-process. So we add up a layer of pre-processing before the electronic. So what we do this optically. And we use this concept here of coherent detection, in which we pick up part of the light from the laser, and we mix it with the information coming back from the scene, right? So, and thanks to this mixing, we are able actually to gain, so it's heterodyne detection, so we are able to gain actually where we have an amplification, free amplification of our signal, right? Which means that compared to the CMOS camera, which are only capturing the intensity, we are able to go much higher, right? So this is why we say here that we have a single photon detection. So of course the CMOS will tell you I can also do the same. I have APDs that can do single photon detection. However, they are extremely limited in terms of power they can deal with, right? Well, here we have the free amplification. That's very nice. So then that allows us then to have higher accuracy at longer distances compared to time-of-flight systems. And furthermore, because we plug part of the system coming from the laser, we're only sensitive to this wavelength. That's the only thing we measure, right? So anything else, like the light, night, day, anything else will not be sensed by the system, right? So it means that we are completely immune to any of these lighting conditions, which is not the case for time-of-flight. So if you take, everyone has been taking picture in front of the sun, right? That doesn't work, right? So similarly, a time-of-flight sensor placed in a car in front of the sun will not work, right? And there are countries like Spain where I guess it's important to have a LiDAR that can work also in whatever the weather conditions. Now, furthermore, that was not mentioned at the beginning, the laser is actually, so we don't send a pulse of light like time-of-flight. So what we do here, we modulate the light. So we move them to the frequency domain, which means that anything that moves in the scene, that is a frequency Doppler shift, will be sensed by the system, right? So that's important. So it means that we also bring And us and our competitors, I mean, CLK and IVA, also bring the velocity into play in the equation, right? Which is not the case from time of flight. So all this said, so that's a very nice diagram, that's a very nice concept. This is also very nice for one channel, right? Now, what happens if we need to move to more channels? Because that's actually the challenge. I mean, that's not necessarily a challenge. So the way we implement this, as I said, we implement this thanks to a peak. So the way we do this, we then, not on one channel, but then in multi-channels, we have waveguides. So, and all these waveguides are collecting the light at once, right? Now, of course, you're going to tell me, but then your system, so your waveguides are very small. They are indeed, I don't know, cross-section is like 1 micron, 1 square micron, right, ish. So that means the system is extremely inefficient. That is true. However, we have also some optics in front of the system that allows us then to couple more efficiently the light back into these waveguides. And furthermore, if you remember, thanks to the mixing, we have also the amplification for the free amplification, right? So all in all, the power budget is not too bad. Now, so that's something that we presented already 3 years ago, at Cleo. So that was interesting. That was during the COVID. So it was in West Coast, 3 o'clock in the morning. No one was listening. At least I was presenting a paper, so I'm sure that no one was presenting. But the implementation that we are using still in our Q1, so our commercial product, is that one. So we have on one hand a tree that split the light. So this light coming from the laser that we split across all the channels that we want to measure. And the waveguides on the left part that collect the information, right? And then we mix this light from the laser with the information collected from the waveguides. We mix it out, and we're able then to extract not only intensity, like the time of flight, but also angle, right? Phase. And phase is important because phase, so we go beyond, so we're also able to extract the position information. So not only the intensity information, which is given, it's an interferometer, but the angle, I mean, the position in space of the point, right? And then, because I think that was topics of yesterday's sessions, now, of course, we still have to plug a fiber, one, so it's not a full, so we have an array in this case, but because we need to bring the light of the laser back into the chip, right? So we still have one package stage to put part of the light back into the system, right? So that's still something that we haven't managed to remove yet. And I know, I think Peter yesterday was mentioning no fiber anymore. I'll come to this at some point. We are not there yet. We still need a fiber in this case. Now, so where do we come from? So we come from space, actually. So we had, thanks to two ESA projects that help us significantly to push the product further. So once again, as I said at the beginning, the goal was really to put a market on a product, which we successfully did. So of course now we have a box which is that big, right? Really that big. But then we had traction, right? We have significant traction, like I mentioned, metrology. So typically metrologies, you have systems which are large. So what we did for space was actually very large antennas, so 4 meter wide. So they are large objects that we scan and are able to provide some information in the depth accuracy below 20 microns. So that's what we demonstrated for ESA, right? 20 micron resolution at 4 meter distance. Now, of course, this is a very high-end product, right? So there are numbers there. I'm not sure they are visible, but that means the product, at least the box we are selling, is 150K, right? So, of course, you might start thinking it's very expensive. Now, for this market, this is typically the price range for laser trackers, laser scanners. So, I mean, even if you take a Nikon, this is, I think this is half of the price of a Nikon. However, here what we bring is actually portability. So normally all the other systems are actually very difficult. I mean, if you take an Nikon system, it's very difficult to take it out, right? Well, in our case, we can actually plug this into, I mean, we went to Sweden to measure trees in the snow. We have an application where we measure bridges in Cordoba. So the stuff is flexible, right? However, if you look at the expected sales, right? I mean, if you take this number, you divide it by the price, that's 10, right? So we are still in a market where the demands is not that big, right? So that's still, so we are far away from the automotive, far away from the robotic, far away from markets which are, whatever, I think there were some volumes mentioned yesterday. We are still far away from those volumes, however, that still allows us to eat, right? Now, from there, where do we move? And that's what we introduced at CES this year. So we move towards this ANT series. And here we'll want to focus specifically on the optical head. So what I mean by optical head is emission, reception, electronics. Right, and this was pretty well perceived at CES. I mean, mostly for the form factor, because the box is. I have some pictures later on that shows the actual size of the chip. The box is very, very small compared to. So we come from something which is like this, and actually the sensor head is actually already the third of this box. So we're going to shrink down this box to something which is that size, right? So very, very small. Now, before I move to the small box in itself, so the Q1, and I'm very sorry because I asked Jose yesterday to take a picture. He sent me a very old picture. But you're still welcome to come to Madrid to visit our production line, because this is where we assemble our Q1, so the box that we are selling to customers. And what we did last year, we actually created a pallet line. So that means we have different stages in which all the elements of the box are assembled, right? So the first one on the left will be where we plug the optical readout, and etc. Down the chain, then we have actually the FPGA and second stage, and first page is actually the housing, right? So this is actually where we are able to produce, let's say, one a month of this big box, which corresponds to the market, right? So don't get me wrong, we are not talking about 100 million units yet. But this is just to say that we have already experienced scale up to some extent, right? Now, so the scaling up, yes, the next thing. So, of course, price. You know the price now, how much we sell this thing. Size, you have seen, I mean, the box, you haven't seen it, but it's that way. And the weight for some applications is not compatible with in-cabin. I'm back to in-cabin. But not only to in-cabin, also for market like robotics and, of course, therefore, automotive. I mean, if you have to put the big box in a car, it's not necessarily a space issue. It's more that's. I mean, the price is also not right for automotive. Automotive, to give an idea, it's $100 per unit. Now, so current efforts are going towards scaling up. So, and we focus mostly. That's the presentation we made in CES. Focus mostly on the sensor head. Right? So that's the one. That's when we show there on the top. And the idea is to offer then receiver, emitter, electronics on the same package, right? And then, so, however, in order to do that, we had to move a bit away from the chip I showed before. So the chip I showed before was actually made of silicon nitride. Silicon nitride is okay. However, silicon nitride doesn't have detection on the chip. So it means that we have to push the light out, read out with the inline camera, put the electronic around it. So it means that and therefore the sensor head was actually that big, right? That's mostly because of the limitation of the chip itself. So now we move to silicon photonics, where we can actually detect on chips. So we get rid of the inline camera. And furthermore, we're actually designing our own electronics, which means we also get rid of the inline camera electronics, which is, by the way, expensive. And then we end up with this package. So we have actually an intermediate stage in steel where we keep the fibers, unfortunately for Peter. But the elements of the systems are there. So all the elements are in this box there. So you have on the top corner, you have the electronic real size. It's a real chip. It's a real ROIC. Big flip chip on top of each other. We have the PCB, and then the idea is so we have also a system that allows us to actually get the dispenser glue, get the PCB, place it at the right position, dispense glue, take the assembled pick as it put it at the right position. And then this, I mean, why they're in this box is because then they go to wire bonding, so we don't do it ourselves. We have partners that can take care of this, and in this case they have to do up to 60 wires, right? So we are sampling this across Europe actually to estimate who can do this better than others. But that's real size, right? So to give an idea of the size, so this is a gel pack. A gel pack is that big, right? What is it? 5 by 5, right? Roughly. So we come from a box which is that thing to a sensor head which is 5 by 5, right? Now back to in-cabin. I didn't forget the main topic of the day. Now, so we don't have of course, we don't have a sensor, right? I mean, the goal of the project is still, I mean, one part of the project is still to be able to deliver this to our partner Indeo at the end, and then place it in the car car body, right? Because they have actually their own body in Barcelona, so they could place a sensor. And obviously, the box is too large for that. But we started with the box actually. So so the picture on the right and left are probably missed. By the way, this is José. For those who know José, that's really José. So for the pictures are both maybe a bit misleading. So what we do here is actually just to give you an idea of what we are scanning, right? So this is acquired for a very long time, through let's say a few minutes, right? So we need some minutes to be able to build the point cloud. However, what we did then, we focus on but this is also feedback from INEO, looking at these vital signs. So what we look at, actually, we focus on the chest, right? But in order to do that, then we reduce the span. So we only scan for between 1 and 2 degrees, right? But we have to scan very fast. So in order to, we limit the angular scanning, but we scan very fast in order to only collect the briefing information. So and here we try to mimic. So we do it very slowly. So we inhale, we hold on the breath, and we exhale, right? To give the time to collect the information. And so the nice thing. So don't get me wrong. This is nothing scientific here. It's just for us to demonstrate that indeed that's something that we can potentially detect. So now the data are at INEO, so they're looking into this. But the funny thing is, I forget to mention that, but people are still in the field, are still thinking in terms of time of flight. So time of flight, they have one beam that scans the system. So they only ask us to look at the distance information, right? Which is fine. Huh? Distance information can give you know, by how much your chest has contracted or increased. However, we can also provide the speed, right? So that's something that they haven't started looking at yet, because they come from time of flight, right? So they only know this distance information. So we limit ourselves there, but for sure there is much more to gain out of this. Then I will speed up very quickly, just to keep on the. You might have seen this before, so I will wrap up very quickly, just to keep on the speed and vibration, right? So it's the work that we have been doing in Cordoba. So we installed actually 4 of the system. By the way, it's also to say that we can do more than one system, right? The production line that you saw before, it's something that helps us to do more than one. We have 4 sensors facing the top of the bridge. So what happens is that we sort of, at the end of last year, José went onto one of these big crane thing, right? He has a degree, right? So he's well trained. So he went up to pick up the boxes, because the box with time actually, mostly the glass that's on, the window that's on top actually deteriorated with time, so we had to clean it up and fix it. So now the boxes are back in the field, and the implementation was interesting, because then we in order to cover the full bridge, we actually force the field of view. So in this case, we have a full 60 degrees field of view to cross all the bridge, mostly to gather the points until the end of the bridge, which is not super relevant for the engineers, because what they are looking for is mostly the points next to the pillar, where apparently this is where the information is extremely relevant. Now, I'm not going deep into this, but I mean, what happens is that when the train comes by, all the points along the bridge collect some information, right? And you can see that the further away, so the points, the points are counted from far to close, right? So 120 is actually the one at the pillar itself, right? So that means that you have this is the one which is more sensitive to any vibration, while the one a bit further away sees less vibration where the train passes by, right? So this is actually so the engineer at ADIF can turn the system on and off. So it's not always on. Huh? They use it on and off, at least when a train passes by, in order to monitor the bridge. And the idea is actually to prevent you know, the bridge collapse, right? So the idea is to do preventive maintenance, be able to feed this back into the model, and be able to say, fine, the bridge can still last for 20 years. So current product addresses niche markets. So that's what we do. However, we have the pilot line that allows us to do more than one, right? So we're able to somehow scale up in that sense. Now, the current development are going to smaller sensors, still focusing mostly on the sensor head, so receiver emitter together on the same box. And the idea is, I think I discussed also this yesterday, is to, within this year, to be able to place this sensor head within one of the tier 1 company, right? That's the goal. So 1 or 2 would be even nicer. But that's the goal. And of course, without forgetting the in-cabins, I'm back to in-cabin, also be able to give at INEO a sensor that they can fit actually in a car for in-cabin monitoring. And with this, I would like to thank you for your attention.
Okay, thank you very much, Gregory. Very interesting presentation. Are there any questions from the audience? I myself, I'm interested. How do you distinguish between the channels? I couldn't really get that.
Yeah, that's a bit part of the post-processing. So the collection of the information is purely passive, right? However, once we have the information out, we still need to do some processing. So there is a FFT involved. So this is all done at FPGA level, and then we are able to say which channels come from where, which information comes from where, right? So otherwise, the waveguide itself is just passive, right? So you just collect the information. That's all what you get, right?
Yeah. So all channels have the same wavelength, same laser input.
It's the same laser, same wavelength, yes.
Okay.
I know where you're coming from. So there are some people also trying to implement LiDAR with scanning wavelength system, right? I mean, in Swiss, EPFR, they try to do that. Fine, but that's not what we do. Because that would mean then having also then the extra constraint on the laser. So not only the line with the laser to be controlled, but also be able to cross through a larger wavelength range, right? Which is, I think, difficult on its own.
Yeah. Okay, thank you. Any other question?
Thank you, Gregory. My question is, since you brought the cost of the unit here,
yes,
could you explain what is the driver of this high cost? Is there a specific part that is most costly?
That's exactly. You mean for the box itself? Yeah. So no. So this is not production cost, right? However, we get a large margin on this. But no, the thing is that the market is known and established, right? So if you Google Nikon, you can find the price of a laser radar, the way they call it. If you go to Leica, you will find also the price of a laser scanner. So our goal, at least as entry, as a newcomer in the market, was not to disrupt the market, right? That was not our goal, right? So the price is based on current market expectations, right? Now, that said, that's a very important point. So we are trying to, that's not presented here. So what we are trying to do is to bring actually a Q2 on the market. So Q2 will be more points. What else? Oh yeah, more points. We have a camera on board because there was also this request from people to see, okay, fine, I scan, but I don't know what I see, right? So we'll have a camera on board embark on the system. So there's some improvements. There's going to be a Q2, right? So one marketing approach could be to say, fine, you know what, we have the Q2, now you still pay for 150 for that, and then your Q1 you can get it for less, right? But that's a discussion I would not entertain because I'm not the business unit manager, right? So, but that could be one way to say, fine, you know what, you can get the old thing at lower price, right? That if it makes any sense marketing wise.
Okay, thank you, Gregory. Let's thank the speaker again. Then it's time for the second presentation. I present to you Daniel Perez, who will talk about the second generation of programmable photonics from iPronics. The floor is yours.
Yeah, thank you.
Yeah.
Okay, well, thank you for the invitation for this wonderful Photonic Integration Week. Another year here. Thank you, Pascual, for the invitation and the committee as well. Today I'm going to talk about software-defined photonics, programmable photonics. It has nowadays many different names, but it has something in common. We are talking about the possibility of being able to modify the configuration and the condition of a circuit once it has been designed, fabricated, encapsulated, and so on. When we started with the company already in 2019, 4 years ago, we were using photonic integrated circuits for a while in the group, in the photonic research labs here in Valencia. And we were used to dealing with all these design challenges, fabrication challenges, packaging challenges. And as we have seen during this event, and also during the last 10 years, the maturity of the ecosystem has grown significantly. So nowadays, you can do better things with lower propagation losses, with better packaging techniques, as we saw yesterday. But with the photonics in general, we can bring it to a different level if we allow the system to be reconfigured in terms of functionality. So what we did with the company that has been growing and growing since then, now with 40 employees, very product-oriented, we have been able to grow a technology during these 10 years, accumulating some pre-company constitution and post-company constitution. And we have been growing and maturity this technology as well. The key thing and the company mission at the time was, okay, let's try to create the world's first reprogrammable device. We did so. We take a piece of silicon, we add a lot of photonic actuators, and we are going to explain a little bit how are we using this technology to basically apply that to different applications. The objective was clear. Let's create a product that can be used similar to an FPGA in electronics to different applications and market needs. On a hardware point of view, we took, as I mentioned, a piece of silicon and created an architecture that basically aggregates a programmable core that allows you to move the light and configure the splitting factors and the phase of the signal at many different local points in the circuit. You can also extract signal to get some feedback monitoring. So together with the optical I/Os, optical interfaces, and these high-performance building blocks, we can create this kind of reconfigurable device. In order to do so, you also need something that was not taking a lot of attention in the past, that is software layer, algorithms that allows you to, first of all, calibrate this complex architecture. Secondly, being able to configure it in an automated way. We have had always our customers in mind, and not all of them has a photonic background or a physics background. So we have been creating during the years abstraction and abstraction layers, allowing people to define circuit configurations, like for example, for an interconnect, rather than getting to the design, the fabrication, and so on, getting a single line of code and automatically getting the system to configure the device. So putting this hardware plus the software and making it work through very basics, fundamentals of the technology. Like for example, this is what we call programmable unit cell, is the way our kind of transistor, if you like to call it like that allows us to generate different states of the circuit configuration at the local level, and then by grouping together more and more of these units, we can create more complex things. This is the most simple interferometer, a match-sender interferometer, where by tuning one of the phase actuators, you can configure the splitting factor, like we are seeing here in the image, from a cross phase to a bar state and a tunable capping state. So if we group these ones together, like for example in this hexagonal pattern, we start being able to basically take a signal from one side of the circuit and then moving it, let's see, and moving it through the circuit. Like for example, in this case, this was in cross state, bar state, and cross state. So we can start creating the light path on real time. By grouping these ones with more and more densities or more integration, being able to put more of these programmable unit cells in the device, like for example in this hexagonal lattice, we are able to define circuits. For example, you can think about, I mentioned before, an interconnect. So being able to configure the circuit to basically allow the light path to follow a specific length. As you know, when we are designing a photonic integrated circuit, it's really important to manage the length of the device, but also the phase. And by suitable programming each of these building blocks automatically, we can basically manage all these kind of physics behind the circuit configuration. You might be thinking about a little bit more complex device, like for example, a beam splitter. In this case, if we configure the channels like this, like cross state, bar state, we can define this light path. And this one can be tuned in a splitting factor state between 0% and 100%, basically defining what we will call an optical beam splitter. These kind of decisions in the past were done kind of manually. So our users has had, the first users we had basically had to program each of these building blocks almost manually, like, okay, this is the status of this one, the status of the other. But as I mentioned before, we have been growing more and more layers in order to automate and make the user's life easier. If we consider all the different technologies and layers that we have developed during the last 10 years, we get this kind of graph where we can see the different technology layers from the pure bare silicon device and the integrated design that you can find there, composed of bends, splitters, tunable couplers, and so on. Then going a little bit higher, we can see the photonic processor as a whole. Then we start to combine together these components. We build circuits with certain complexity. Then on top of that, you need to have your firmware to drive all these actuators. But at the same time, as I mentioned before, to close the feedback loop, we also integrate the necessary technology to read out at 300 microseconds speed the signals from on-chip photodetectors. So by being able to have direct feedback allows your system to automatically create, or you can create automatic routines that basically compensate physical deviations, environmental deviations, and so on. Having these drivers, the firmware on top of that, then allows us to build the necessary automated layers. As I mentioned, it could be modules or more advanced application-specific algorithms that build on top of the system, allows, again, our goal, which is basically democratize a technology, so making it much more accessible from one side. But for the other side, and after 4 years being in the ecosystem, talking to customers, getting real and direct feedback, one of the things that we have been doing almost continuously since we started this journey has been basically trying to see where else this programmable or software-defined technology can be applied. It's nice to have this general purpose processor, and a very personal opinion, I really believe that in a relatively short time frame, the technology is going to improve and improve to reduce the form factors we have today, to increase basically the versatility power of this, being this as pervasive as FPGAs or microprocessors are today. But in the short term, there are also different markets, needs, and applications that can be solved. Before jumping to that, just to touch a couple of points on the additional IP that we have generated. Evolving from these circuits, we also found that there are some circuits that are not done optimally in an hexagonal mesh discretization. So it's always handy to have on your chip some IP blocks, some extractors, like for example, WDM filters, dynamic beam splitters, full advanced filters, and so on. So pieces of silicon, pieces of application-specific devices that can be used for additional number of applications. If this is connected to your mesh, then you can basically expand the possibilities of the functionality of the device. What we did, as I mentioned before, is putting all this together into a box. It's called a Smart Light processor. It's shipping since 2022. I'm seeing here in the audience some happy customer faces. And also, it's beyond what I mentioned before. It's a tool basically at its current status as a product that is being used in most of the cases for basically some people use that as a paper machine. It's a very good way to demonstrate proof of works, proof of concepts very fast, in a matter of seconds or weeks. If you need to think a little bit about your idea and how to execute that, you can basically demonstrate relatively advanced concepts. We have seen many examples from one of the customers, like Nokia Bell Labs, demonstrating Hamiltonian photonics pretty fast. So it was during a 3-month time frame, they were able to demonstrate and publish really nice results. Beyond this, I really believe that this is also a really powerful educational tool. If anyone here is coming from the university, it's a very good way to understand the physics behind photonics. So with the cathedrals and the PERTES stuff, it's a really new addition to your lab portfolio. And just to finish with the smart light piece, we really believe that the combination of this photonic processing combined with high-speed modulators, high-speed photodetectors can expand the number of functionalities. There is a nice publication that we published 1 month ago that basically aggregates these smart light processors as the core of a processing system, and when combined with additional building blocks, could be employed to demonstrate advanced functionalities in 5G signals transmissions and orchestration, arbitrary waveform generations, tunable delay lines, optical filters, and so on. Okay, just making a brief pause here, I'm going to jump to what we consider the next generation. As I mentioned before, the technology that we have been building during the last 10 years, it's a really nice technology for general purpose photonics engines or processors, but we are really encouraged as well to address some of the challenges that we see in society. There are many companies, many startups that have tried and continue trying addressing challenges like, for example, computing, AI, quantum photonics, and a big portion of the solutions that these kind of companies are providing are based on being able to master and configure a big number of photonic actuators within a chip, or what we call software or reprogrammable photonics. One of the challenges that I wanted to highlight today is based on the data center. As I mentioned before, AI computing in general is growing and growing at a path that is, I will not say unsustainable, but almost. And I think it was last year when, for the first time, intra-data center traffic is higher than inter-data center traffic. So the traffic that is within the data centers, within all the servers, is expanding at a rate which is way faster than the data that is getting in and out of the data center. In that sense, if you take a look to data centers today, you can see some problems. I have tried to summarize a few of them here, and I can just verbalize a couple of them. The first one is related to future-proof architectures and CapEx. We have, as you know, most of the data movement in our lives today basically relies on thousands of millions of transceivers in a single data center that basically joins 2 points, electrical points. You have a transceiver, a piece of fiber, and then another transceiver connected to an electronic switch, and then connected to another hundreds of electronic switches. These kind of optical interconnects that actually are connecting 2 electrical points by optical means, their main characteristic is that the data rate capacity is doubling every 2 years. However, the technology that interface these kind of transceivers, the electronic switches, are relying on SerDes that basically double their data rate capacity every 4 years. So you can anticipate more or less the problem that is already present there and the problem that is about to come. Another one that is shocking is the energy consumption of data centers today is around 3% of the power generation capability of the planet. And according to the predictions, in 2030 is going to be the 10% of the energy consumption. So 10% of the world energy consumption coming just from the way we move data within a data center. Just showing this kind of problem, a quick introduction to data centers is you can see that what I described before, these electronic packet switches connecting the information between the servers within the data center. And the thing is that most of the data that was within the data center from 2010 and before, was based on packet switching, so basically small bits of information that travel through the data center with packet switching. However, we know that the data that is generated due to computing or AI, basically it's much more predictable. Most of the work done on this has been from Google. Google invested more than 1 billion in the last 13 years on trying to come up with solutions for their data centers and anticipating these kind of bottlenecks. Their solution is relying today in MEMS, so it's photonics, optical switching for circuit switching, but in this case relying on micromechanical structures. So the way we propose to solve this problem, similar to Google, is being able to address a differentiation between electronic circuit switching, electronic packet switching, but at the same time optical circuit switching. So aggregating into the data center optical switches that basically allows us to interconnect computational resources directly in the optical domain without the need to transition again and again and again and again to electronics, optics, electronics, optics, electronics, optics. One way to achieve this, and as a link to this presentation, is through programmable photonics. In a way that what we are proposing is being able to basically have a core and programmable photonic engine that allows you to perform this switching operation that today is being done with MEMS, but rather than taking milliseconds, tens of milliseconds, being able to reconfigure it faster, so allowing you to re-optimize the data center architecture in microseconds time, but at the same time having a future-proof technology. So I mentioned before that data rates are increasing, so a few years ago we have 20G transceivers in the data centers, then 100, then 200, then it was too expensive for most of the people to jump to 400, and then now people is starting to jump into the 800G, and then the 1.6, and then the 3.2. So basically the data centers requires an upgrade every cycle of normally 1.5 years to 3 years. So having a technology that allows you to keep the technology for several cycles is also a cost-effective solution. So yes, a quick way to address this challenge with photonic integrated circuits could be having a programmable photonic engine allowing you to basically have not only this switching operation, but at the same time start moving some of the photonic processing to the optical domain. I think it was this year at Photonic West, but also last year at OFC, where some companies are already demonstrating the possibility of using, for example, optical filters in the optical domain to compensate, to equalize the channel, and then reduce the number of operations that one of the most power-consuming devices in a transceiver has, like the DSP. So being able to do some pre-optical processing in the optical domain versus doing this kind of all the processing in the electronic domain is one of the ways to address this issue that I mentioned before of the world energy consumption. Just as a quick view of what this implies and what are we doing at Ipronics, we are creating probably one of the most complex devices today, but the plan that we have is not getting easier. One thing that we have learned during these 4 years within Ipronics is how to master complex photonic integrated circuits, but not because of the complexity, because complexity is the price that we are paying in order to solve problems like how to have basically low insertion loss device, no blocking optical switch, low power consumption device. There are many, many ways to do that, and one of the ways is basically paying a price, which is mastering complex photonic integrated circuits. You can find here a quick view of our plan. As I mentioned before, it's not getting better in terms of easiness. You can see here the two silicon chips, the two generations that we have in the market today. Actually, it has around 500 actuators, but in the main circuit are the ones that we are counting here on the graph. And as you can see, our growth is going to be even more than doubling the number of actuators per year. Why are we making it? I mentioned it before. We are making it possible by mastering how to have low loss in the circuit, mastering the crosstalk, the high integration densities, basically to being able to integrate more and more. One that I like to refer to here is, for example, you can see that for the different generations that we are going to do, the number of programmable unit cells that we are integrating, I think that today, in most of the circuits that you can find, is 0 point something. In the ones that we are performing today, we are approaching already the 4 programmable unit cells per millimeter, but in the next generation, we are aiming for 17 and then 71 match senders in a millimeter by millimeter area. And the thing is not about putting the match sender there. It's something that we can all do today. The thing is being able to put them there, make the thousands of actuators to work cooperatively all together and talking together without having crosstalk, but at the same time having a good insertion loss power consumption trade-off. And just to finalize, I'm showing a graph that I think that I showed last year. It should be updated, but it's a way to show you that we are not crazy. So technology maturity, what I mentioned at the very beginning of the talk, it's basically allowing us to achieve these kind of targets. Of course, through considerable investment in talent as well, and with a powerful team working on this direction. But you can have a feeling of the growth of the technology maturity if we see under this analysis of different works published during the last 20 years, where we have basically point to the number of actuators that we as a community has been able to integrate. The first category is other or reconfigurable optical devices. Here we consider reprogrammable filters, beamforming networks, and so on. And you can see that, okay, it's the amount of actuators is definitely growing. Then the feed-forward meshes, mainly used for computing approaches and quantum photonics. Also starting in 2015, but growing very fast and benefiting from the prior technologies. The general purpose devices, the one that I covered at the beginning of the talk, and then the optical switches probably are the ones that since 2015 started to dominate, and the ones that we predict that is going to be one of the key market drivers for this kind of complex integration. If you take this chart, you get that most of the devices are following this, doubling the number of actuators every 2 years, and this kind of trend is the one that was supportive the internal Ipronics plan. Some scary figures, and I think that they are going to be even more scary, is 10,000 actuators in less than 3 years ahead. I think that there are some publications that are already touching 8, and I think that it's going to be in a single year where we are going to see some of these regular publications and products based on this kind of technology. But the scary ones are coming like more than 100,000 actuators in less than 8 years. Again, I think that I'm being very, very conservative, and our challenge as a company is we are going to be on that scale much earlier than that. How to do that? Basically, you need to have control electronics that are scalable. You need to have a software layer that helps you to solve some of or mitigate some of these challenges associated to the optical loss, the crosstalk, and so on. But at the same time, the software layer per se is another challenge. You need to invest the necessary resources to make that possible. A quick comparison with electronics, we are like in the 70s, more or less, in terms of integration densities, if we compare photonic actuators with transistors directly. But putting the focus on these specific challenges, and then closing the talk with that, is with electrical connections, I had very good memories when working in the lab using proofs, multi-contact proofs that we use to demonstrate what we consider large complexity designs. It's something that you can use until few dozens of electronic IOs, and then you start jumping into wire bonding. Wire bonding, one thing that I learned is that you can put wire bonding to the limit, having up to 4 or 5 rows and very high integration densities. But normally you use them, and we can see that in the graph, up to 500 interconnections, and beyond that you need to start jumping into flip chip. That of course has many different variants and is already a mature technology in electronics. The thing is, the challenge about making these compatible flip chip technologies with the edge coupling that you need to accomplish after that for the optical fibers. Regarding the control electronics, again, very good memories when driving our first devices in the lab, having bulky control electronics to address these drivers. And then, as you can see in the literature, this is fine for the first 100 IOs, and then from 100 to 500 IOs, you start needing board-based devices or specific designs to address this. And this is something that, honestly, I believe that can scale up to 8,000 actuators, more or less, and then beyond that, probably monolithic approaches might be a must in order to reduce the number of IOs. And just to finalize, regarding the physics behind the actuations, depending on the speed that you need, depending on the complexity, you might want one or the other. But the true thing is that 90% of the works today employs thermal optics due to their simplicity, due to their ability to provide lossless operation when passive and when active, and due to their robustness as well. So, yep, I hope that this has served as a good introduction to programmable photonics, and I'm happy to address questions.
And thank you very much for this both interesting and promising presentation. Are there any questions?
Yes, very nice presentation. So just one thing. So you mentioned the power consumption. You say it's 3% and 10%. And you also mentioned it's mostly thermal-based thing, right? So what is the power consumption of these 4,000 actuators together? And if I make a parallel to LiDAR, so you also mentioned beamforming at some points. I mean, there was something very popular at the time in LiDAR, which was the OPA, right? But all the companies busy with this thing, they stopped, right? Because of power consumption, because the stuff was turning into a heater, right? So similarly, what is the power consumption of these 4,000 actuators together, right? Put together?
So thank you for the question. Regarding power consumption, similar to the overall technology maturity and growth, we have some as well, like even, for example, thermal optics, the one that I highlighted as the most employed ones. The first thermal optics in silicon photonics consumed around 100 milliwatts, and there has been more than 2 orders of magnitude reduction in the last 10 years. So nowadays, each actuator consumes around 1.3 milliwatt. You can get that kind of optimization. And regarding the question on the 4,000 block, the 4,000 block that I have shown there, that was a switch, has 2 characteristics. First thing is, even though we are integrating 4,000 actuators, that doesn't mean that for the operation you need to switch on all of them together. So it's kind of a sparse design. I will say that a low percentage of them are actually switched on, but the overall power dissipation that we expect from the actual chip is really, really small compared to the dissipation of an electronic device. And putting numbers, we might be talking about less than 1 watt or a couple of watts for the peak per se. And then the overall power consumption of the unit should be way below, I would say 200 watts, but for a rack-based units as the ones that we are seeing here. For a LiDAR optimization, it's most of the power consumption today comes from the need of keeping a temperature of operation. If it's wider and wider, then you will need to support a system that allows you to dissipate all that power from the device. So overall numbers, I will say, for example, the smart light unit that I presented before that has several hundreds actuators, the typical power consumption is lower than 20 watts, and is a device that is not fully optimized for power consumption reduction.
Hello, thank you.
Okay.
Okay, thank you. It was a very nice presentation. Now it seems that you are, or you are maybe one of the products, you are focusing it more to switching stuff. So do you still maintain the same kind of topology, or are you, I mean, how does it compare with traditional stuff? I don't know.
Yeah, so very good question. For the general purpose device, we optimize the architecture to keep flexibility, versatility, and general purposeness. For the optical networking engine challenge, what we are keeping exactly the same is the layer stack of technologies, the same components, the same electronics, although, of course, we are advancing in the next generations. But for the layout per se, for the circuit configuration, we have optimized the circuit configuration for this specific market. Although same components, but different structures and aggregations. Yeah, one of the things with hexagonal mesh is beautiful for multipurposeness, but when it comes to switching, it's a arrangeable non-blocking in some cases. It's not fully non-blocking, and we need it fully non-blocking, and that's the architecture that we optimize for.
Thank you for your talk. There is this trend in using non-volatile phase change materials for programmable photonics. Do you see this as a thing that will happen, become a mature technology, or it's still too early and experimental?
I think that today is too early. At least the work and the progress of the work, it's still limited by the resolution that you can get with the phase change material. The control bits that you can achieve, if I'm not mistaken, is around 4, while in the thermo-optics devices you are in 12 bits or so and so on. And this basically affects when you are programming your device into bar or cross state. If you don't have enough resolution to go from one state to the other, this is the origin of optical crosstalk. So when a new technology gets as a solution, we need to identify what is the actual benefits that this technology is bringing compared to the existing solutions. The existing solution today, the most popular at least, is thermo-optics, and the problem for other technologies to basically jump into thermo-optics is that you need to beat a technology that today is lossless, the footprint can be optimized up to 50 microns. I think that is the state of the art, more or less. The power consumption, as I mentioned before, is around 1.3 watts, 2 milliwatts, sorry. So it's really low power consumption, lossless, impassive, lossless during operation. Probably the only concern that people might have is crosstalk. And when I mentioned jumping from 4 match senders in a millimeter square versus 74 match senders in a millimeter square, thermal crosstalk might be a potential issue, and that might be the opportunity, the room opportunity for phase change material, but only if if this technology can at the same time provide this lossless, which is vital for evolving this kind of programmable devices.
Thank you.
Okay, thank you very much.
Yep, thank you. Okay.
Let's thank the speaker again. Okay, then let me introduce Pablo Guinel from AG Photonics. Pablo, the floor is yours.
Thank you. Hello, everyone. I'm Pablo Guinel. I'm a strategy and BD manager of AG Photonics. First of all, I want to thank Pascual for the invitation because this is the first talk that we do in public in front of the photonic ecosystem. So today I'm going to talk about AG Photonics, what we do, and what is the product that we want to develop related with the advanced transceivers for future optical wireless communications. Oops. So we come from Malaga, South Spain, and we are a spin-off of the University of Malaga. Specifically, we come from the School of Telecommunication Engineering and the research group of the Photonics and RF Research Lab led by Íñigo Molina, who talked in the last session. We were founded in May 2023. I was still finishing my PhD in that time. And the team that founded the company was formed by the academic promoters of the Photonics Research Lab and some former PhDs of the same group. Actually, we have seen this month the Series A investment led by Bullnet Capital, who is going to support the project for several years. So the team of founders that compose AG Photonics is formed by 3 co-founders that work full-time inside the company. The first one is me. I'm the expert in the design of integrated optical antennas in silicon photonic platforms and optical phase arrays. Alejandro Maes is a photonics engineer with more than 10 years of experience working in research institutes around Europe. And Dario Sarmiento is PhD in integrated photonics, and he has also a lot of experience in the design of coherent receivers. He has more than 6 years of experience in different technology companies, different from photonics, which is important also. And in the academic part, the academic promoters are Íñigo Molina, Alejandro Ortega, Gonzalo Bonbemer, and Robin Jalil. I think that you know all of them. They come from the Photonics and RF Research Lab. We have a lot of milestones in the academic area, but also in the industrial area. They have more than 20 years of experience in research of radio frequency and photonics, more than 100 publications in journals of high impact, a lot of doctoral theses, and research projects. And also they have recognition in the Stanford ranking as academics from the world with more seats in the world. Also in the industrial area, they have worked in the commercialization. They worked in the commercialization of the first photonic coherent receiver for U2T and Finisar. They also designed microwave devices for 84 wireless, which now is Keysight. And one important thing that they do in the research group is that all the research that they do, they try to protect by they try to protect intellectual property by filing patents. We are the second spin-off of the group, and we are trying to make bigger the photonic ecosystem of Malaga. Actually, in the company, we are only 4, but in the short time that we have lived in the company, we have achieved a lot of things. We are part of the ranking of this top 100 startup 2023, but also we have received 2 misiones per the chip. Only 4 companies in Spain are working at the same time in two projects inside the framework of the misiones. And also we have made a lot of noise in the national press and news. But this team of 4 people, what we are doing and what is the problem that we want to face with the product that we want to develop. So internet is actually not available for everyone in the world. More than 2.6 billion people remaining connected. So that represents 1/3 of the world population. And also the people that is connected or can have technology to go to use internet and mobile devices generate more and more information. So it is estimated that by the end of 2030, the information generated by mobile devices and internet is going to be 20 times greater than the information that is generated now. So the data volume is going to grow exponentially, but also there is another problem that is related with the power consumption. The power consumption in data centers is going to grow also exponentially. So it seems that it needs or we need to expand the actual, the current infrastructures and the actual networks with new type of technologies that can help in these two problems. Actually, the current solutions or the current technology, the two main technologies that are used are, the first one is the optical fiber. With optical fiber, you can transmit a very high volume of information in a single guided medium, but it has some problems because you need long deploy time. You need to bring the fiber to the end user one by one. Also, it's not reachable. Optical fiber can be used in urban areas, but you can't deploy the fibers in rural areas or outside urban cities. And also, it has a high cost deployment. You have to do constructed, like you can see in the image, and there is a high price in bringing fiber to everyone. Where the fiber is not capable to reach, you can use radio frequency links. This is the main technology used for wireless communication, but also it has some problems like the data rate. Radio frequency links are not going to support the volume of information that is going to be generated in the next years. Also, you have to use a spectrum that is with a license. You have to pay for the use of some frequencies. And also, there is a lot of interference. So they say that these type of links are not secure. So you can do a type of spoofing, or you can detect radio frequency signals. So there is a technology that is going on, and there is a lot of people working that is using optical wireless communications, not to substitute this technology, but just for expand the network infrastructure and help and support the actual technologies. Optical wireless communications offers some advantages, like the higher bit rate, because you are using higher frequencies. Only the visible spectrum of the light is 1,000 bigger than all the spectrum on the radio frequency communications. Also, you can achieve higher directivity channels with smaller radiation apertures. That is because the wavelength of the optical communication is much shorter than the radio frequency ones. And they don't need to regulate the spectrum. You don't have to pay for that. So the time to market for operators is shorter than in radio frequency. And also, because of the higher directivity and a small divergence of these links, they say that this type of communications has a higher level of security. So the idea of using optical wireless communications, as I said before, is not to substitute the actual technology, but expand the infrastructure. We can see in that image the future scenario in an urban area where you can see that in the land layer, all the connection can be made by optical fibers, but also in several layers that are going to appear. People are talking right now of new layers that are called high altitude platforms, intersatellite communication, and so on. The radio frequency is going to be used, but also the free space optical communications. So our proposal in AU Photonics, we want to develop integrated optical transceivers for these free space optical communications. And to that, we are going to use all the know-how that we have in the design of integrated devices in silicon photonics, but also a lot of know-how that we developed during my PhD in the last years that is related with the design of integrated optical antennas and optical phase arrays to achieve a dynamic pointing and track between an emitter and a receiver. So there is a lot of project right now developing this optical transceiver. For example, here in the image, we can see the Tara transceiver, which is the optical transceiver that is doing right now Google. I talked with the team last week in the Mobile World Congress, and they were amazed with the technology that we are developing in Photonics. The idea is to substitute all the optical and discrete optics that you can use here for that. We can integrate radiation apertures to emit and receive, but also we can integrate modulators and coherent receivers in the same chip. So we are gaining all the swap advantages that are reducing the size, weight, and power consumption of these devices. The know-how is, as I told before, is related with the most important block in the product is the interface between the chip and the outside world. That interface is going to be done by the use of these optical phase arrays and antennas arrays. This is not the actual solution that we are going to use in the final product. This is the proof of concept that we did during my PhD, and it works very well. We learned a lot about these integrated antennas, and this was the first integrated optical antennas developed in silicon insulator with a larger minimum filter size. So it could be, we always think into adapt these designer solutions into to be made in foundries that are not only using E-beam, but also deep UV. So with this miniaturization of the antenna, we can achieve extremely directive wireless links with more than 70 dBi, and without the need to use very large areas. So the reduction of the SWAT parameters, size, weight, and power consumption, is going to enable this technology for the typical application of optical wireless communication, but also for new applications that are going to appear in the next years related with dynamic scenarios, as I will show later. So with this technology, we want to offer an integrated optical transmitter with a very small form factor, a reduction of cost, because these chips are the costs are going to be reduced because they are compatible with the CMOS fabrication processes. And also, we want, by reducing the size and price of this product, we want to make easy the deployment and quick the deployment of these optical links. So what are the typical applications of this technology? The first one is to use this optical wireless link as in the backhaul of mobile networks, not by substitute the actual technology, but also for assist the RF links, and to transmit by wireless connection more data rate than with radio frequency links. Another application is the last mile connectivity to achieve or bring high data rates to areas where the optical fiber can reach. For example, in urban areas very far from the city or rural areas, but also to make private networks for enterprises or for governmental buildings. Also, the optical wireless communications are going to be used for emergency network assistance because of the quick deployment of these networks. They are going to be used for the backup of the current technologies, and also regarding the problematic of the people that were unconnected to the internet, to facilitate the access to this technology by deploying cheap wireless networks where the optical fiber or RF links can reach. Also, in the part of security, there is a lot of interest in defense areas for the use of these optical links, because these optical links are difficult to be detected. And also, they are barely any interference between transmitters because of the very high laser pulse between emitter and receiver. And another application that is now A very hot topic is the inter-satellite communication and non-terrestrial networks. In non-terrestrial networks and 6G, they are not going to use optical links, but last week in the mobile, I learned a lot of things. Talking with operators and different companies, they say that they are not going to use these optical links for the mobile devices and so on, but all the communication between the high altitude platforms or all the communication between the satellites that cover some areas of the Earth, they want to use these optical links. Also, for example, Starlink recently published that they are using more than 10,000 optical links right now, communicating between their satellites in LEO meshes. And this reduction of the swap parameter can enable this technology for this type of applications. So what is the roadmap of what we want to do in the next year? By the end of 2024, we want to have all the photonic integrated circuit developed and tested in a laboratory area. So we want to demonstrate the integrated coherent receivers, the integrated modulators, also the optical phase arrays that are going to have steering electronically without the use of mechanical systems. And also we want to demonstrate these optical phase arrays with auxiliary antennas that are used for all this thing of the pointing between emitter and receiver. By the end of 2025, we want to reach the minimum viable product, which is going to be integrated transceiver with all the encapsulation and all the electronics. So we want to make a big effort in the design of all the electronics that are going to control the pointing and also the modulation and the modulation of the signal, also the optical packaging around all the product, and the algorithm needed for making the connection. And by 2026, we want to reach the first commercialization of this product. That is not going to end there because we want to work in a lot of research around this product because we want to achieve dynamic pointing and track for this dynamic application and making larger the field of view, for example, or work in the polarization and power management inside this chip, or also a topic that is we are very interested in working on is to do all the phase correction with these integrated optical phase arrays. This is related with all this thing of the turbulence mitigation without the use of deformable mirrors and waveform sensors. So there is plenty of room for the future upgrades that we are going to apply in the product. Mainly the first or the minimum viable product is something like this. I like this figure because it seems that it's easy to do. Yeah, there are some boxes with colors, but we want, by the end of 2025, we want to make a lot of effort in the blue. By the end of 2024, sorry, we want to do a lot of effort in the blue box, in the photonic integrated circuit, and by the end of 2025, we want to do, or we want to have complete all the things that are around this photonic integrated circuit. Also, in this first stage of the company that we are very focused in the development of these photonic devices, we are doing some services of ad hoc design, and we are participating in some projects. These are the two mission expertship that we are participating on. One is Enlace, led by Fila Lasers, and the other is Impact, led by Biohelium. In both of those projects, we are in charge of the design of integrated passive optical devices. Also, we have done some design services, for example, for the Universidad Politécnica de Madrid, and now we are in collaboration with a very big quantum company doing some passive integrated devices. So that's all, and thank you.
Thank you very much for your presentation. Are there any questions from the public? I see one.
Well, first of all, congratulations for your achievement. Second, I'm terribly curious to know how you handle the alignment between transmitter and receiver, because basically between two satellites that you have several thousand kilometers, between two radio links that they might be 5-10 kilometers away, you go away with the high directivity that you have 1 degree or 2 degrees, or you are out. How do you manage the alignment between transmitter and receiver?
Well, that's a good question that I think we are in a very early stage to answer that with very specific information. But the important thing is that we are going to aim first Earth-to-Earth optical links, because space links has a larger time to market to prove the things there. But the important thing of this is that you are not only using the transmitter optical phase array and the receiver optical phase array for the pointing. So that's why you are using those that I mentioned, auxiliary antennas, that tells you the direction. They are like DOA systems. They tell you the direction of the arriving signal that you are receiving, and then you tell the OPA where he has to send information or where he has to look as a receiver.
Okay, any other question?
First of all, thank you very much for your talk. And my question is very related with his one. What are the expected distances between link distances, or in other words, what's the noise? How does the noise affect to the link, or what are the expected losses or the noise floor of the photodetector, let's say?
Well, by doing the power budget and designing your antenna to have a specific directivity, we want to aim optical wireless links of around 10 kilometers. So you do the calculation, you need to emit some power, you know that you have your directivities, and that should work with the power budget.
Okay, thank you, Pablo. Let's thank the speaker again. Okay, then it's time to welcome the last speaker of today. We have with us Carlos Pardo of KDPOF. Carlos, go ahead.
Hello, good morning. Pleasure to be here. My first time to join this group. Really appreciate I'm invited. I still feel myself like the ugly duck, looking to the presentations I have seen with this fantastic integrated photonics. Our products are much, much simpler. But it might be of your interest, so that's why we are presenting it. So I hope you will like the presentation. So I'm going to do a very short company presentation so you understand what we are doing and also the projects for the future. The main, as some of the presentations, my first recognition is to the team. Without a fantastic team, that's impossible to be achieved, what we have achieved. I'm going to spend some time explaining the history because I think it might be of your interest, how during all these 14 years, what we have been able to achieve. I've been doing semiconductors all my life, and we launched the company in 2010. We were focused initially on developing plastic optical fiber transceivers. Now we are also in the glass fiber world. We get the first investment also from Bundescapital in 2011 together with Caixa. We were having our first silicon in 2014. One of the good things that we have been able to do is to standardize the technology that we develop. It has not been easy. We started standardizing in Germany, then we moved to ETSI, the European standards, and now we are standardizing our technology in the IEEE. And we have two technologies, and they are pure Ethernet standards in 802.3, which is, as I normally say, we are playing in the Champions League, where all the Qualcomm, Broadcom, and Marvell are standardizing their technologies. We were able to standardize our own technology. The first technology that we developed was for 1 gigabit transmissions over plastic fiber. As for you that you may not know, the plastic fiber is a polymer fiber with 1 millimeter diameter, where, as you can imagine, the bandwidth of the fiber is very limited. We were using LEDs, not lasers, so that's why our products are much simpler. But achieving a gigabit in a LED, which is limited in 80 megahertz, and a fiber, which is also limited in 100 megahertz, was not easy. That was standardized, and we are in production. Now we have been able to standardize our new technology, which is trying to address up to 50 gigabit per second using OM3 fibers, multi-mode fibers. Now we are using VCSELs. And we were able to publish the standard, I think it was a year ago or something like that. And yeah, we are focused mainly in the automotive market, because when we started the company, we were addressing different markets, but the one that we are having more success is the automotive. In 2019, we have our first car in the street from Daimler, now Mercedes, using our technology. Now we are selling millions of chips every year, and the amount of cars using our technology is growing every year. Now we are expanding also to China, and it's really, I really feel very proud when I see cars in the street that they have our chips. That's something, it's a fantastic feeling that hopefully will increase and increase. Yeah, let's continue. Well, I'm just a co-founder. My colleague Ruben is the intelligent person of the company. Myself is just trying to get money, my main task. But what I think is important is that one of the things that we have been addressing during all these years is rethink problems again. Normally, people were telling us this is not the way that things has been done for years. Don't reinvent the wheel. You have to do it in this way. What we have been doing during all this year is rethinking again and again the problems, and we have been able to provide solutions that are simple, cost-effective, and that's why we are now in production selling millions in cars. If we follow the path of just doing the same thing that has been doing for many years, we will not be having this success right now. So that's why I think it's important to show this, that rethinking, being very strict in the analysis, very, very analytical, how we should provide a solution is what I think is a key factor for our success. And trying to explain our product, we are addressing the in-vehicle networks. This is a scheme of in-vehicle network of the future. Right now, they are not like that. They are much more complicated. But we are trying to reach this point. Why? Because right now, the current cars they have kilometers of cables connecting many sensors, many electronics to the central ECU. Central ECU has huge amount of connectors. The amount of data that is being transmitted is growing exponentially with autonomous driving, with cameras, radar, lidars. And so the car is restructuring itself slowly because, as you know, the automotive industry is moving slowly, always. But they want to achieve this type of architecture. They call it the zone architecture, where you try to aggregate traffic from different sensors or actuators, and you concentrate that traffic, and you centralize the processing power in a central ECU, maybe 2 central ECUs, and then if you have, this is our autonomous car, then typically this is another electronic, which it needs to share all the information generated in the car to be able to process. That means 8, 9 cameras, like 2 gigabits per second or even 6 gigabits per second per camera, radars, LiDAR, infrared sensors. Everything is being analyzed by the same CPU, which means today there are already cars which are receiving 10 gigabit of information from sensors, and then several 2, 3, 4 gigabit per second cameras. Everything is being processed. I remember the first prototype of BMW, they have a 10 kilowatt CPU processing all the information that was received by the sensors. 10 kilowatts is what you need to move a car. So you need the same power to move the car and to process the information. That has been improved with NVIDIA and Qualcomm. They are reducing the power for sure, but as you can imagine, the amount of power required in a car for all these intelligent cars is incredible. And all we can do to minimize the power in the transmission and simplify, aggregate the amount of connectivity of those chips that are analyzing all this information is important. We are providing such links, typically the very highest speed. The lowest speeds are typically copper, and the very highest speeds are optical. Here we are showing how many links you may find in those cars. So as you can imagine, we are selling today the full world like 90 million cars. If you multiply by the amount of links, the amount of total ports that you need is incredible. And this is the market that we are addressing. Why the industry is moving from copper to optical? First, I would like to say that the industry hates optical. They don't like it at all. The automotive industry, they prefer copper. They know it, they can touch it. They have been using copper for decades. Moving into optical is complicated for them. They need to learn. They need to analyze how this has to be managed in the repair shops, how to manage that in the assembly lines. That's not easy. They need to move the full industry. So they are trying to avoid the jump into optical. We are leading worldwide that effort, and we are convincing the OEMs. And what is in favor of us is that they are reaching the limits of the copper. They are addressing a lot of EMC problems, a lot of electrical and galvanic isolation problems with electrical cars, but also the copper lines are reaching the limits. And in the same way that in data centers, they move from copper to optical when you increase the distance or you increase the speed, in the cars, the speed is forcing them to move into optical. That's our products. Now what I'm trying to explain what is our future, what we are doing. This is really driven by the fact that we are being awarded by the IPCI. We are one of the only 4 companies in Spain that we have received this IPCI grant as direct project leaders. There are others that they are receiving that award, but they are behind us in timing. The IPCI is a project funded by each country of the European Union, but is allowed by the European Commission. They analyze close to 200 projects. They force many of these projects to join efforts because competition is not allowed within the European Union. to fund the projects. And in Spain, we have, I think, a total of 15 projects, I think, right now. 4 are directs, and the rest are indirects. And they are forcing you to do two things, R&D and first industrial deployment. And we are doing both things. In the R&D, what we are doing is developing the transceivers for the automotive industry. As I said, the technology that we have in production is for 1 gigabit based on plastic fiber. Now what we are developing is technologies for glass fiber, OM3 multimode, and 10 gigabit, 12.5 for cameras, and 25 gigabit, which is not very high for those that you are used to data centers. But what makes this unique is the fact that this needs to work at 125 degrees from -40. The lifetime has to be more than 15 years of operation at these temperatures. The conditions are really, really ugly. That means water, dust, vibrations. The failure rate that you have to have is 0 ppms, where in data centers you may have hundreds of ppms. Now, for us, we cannot fail. If some of these links fails, you can crash the car in autonomous driving. So you cannot have failures. Of course, you have redundancy to make sure that even if there is a single failure, the car can continue driving. But certainly, it's a safety thing, and it's really challenged. Okay, and that's why the standards are new, because you need to qualify for automotive applications. Then you need to equalize. You need to put forward correction, even at that lower speeds, to make sure the link budget is huge. The link budget we are operating these technologies right now is more than 20 dBs. We are allocating 2.5 dBs per connector, which, if you look to data centers, is incredible. Okay, this type of things. But we are not stopping in that speeds. Also in the APCI, we are, and this is our first experience with integrated photonics. We have to provide a transceiver, a prototype transceiver for 100 gigabit, and we are going to pre-qualify that for the automotive industry, and we are going to use integrated photonics for that. Of course, we don't have the know-how inside. We are going to collaborate with a third-party company, but what we are going to do inside is all the packaging, testing, and validation of that. In the first industrial deployment phase of the project, what we are going to set up is production lines. Okay, we are going to set up 2 at least, one for the current project of 1 gigabit, and the other one for the multi-gig, 10 and 25. And also we are going to put some labs that will allow us to do prototyping and qualification. This, I will go more in detail on the production lines later. In this new facility that we are going to set up, we call it Prado because all our projects are painters, Spanish painters. So Prado is where we are going to produce all that. And we are going to have different facilities that will allow us not only to produce our products, but also to do wafer processing, qualification, testing, and so on. This is a draw of our 2 current products. The first one is the 1 gigabit. You can see the transceiver on the right, which is with very big holes. These holes are for plastic fiber. It's 1 millimeter fiber, and it's very, very easy to align the fiber with the LED and the photodiode. We are integrating a single package, an LED and a TIA with the photodiode embedded and LED driver. And this is already in production, but we are bringing the production to Spain. We will be producing both in China and in Spain in parallel to our current customers. And the one on the bottom is the new technology that we already have prototypes and they are working. I cannot show pictures of the actual packaging because it's under patent filing right now. So we only provide you the concept of the package. It's very simple. We are integrating CMOS die, which does everything, all the PCS, PMA, digital signal processing for error correction, but also the laser driver and the TIA in the single CMOS die. We are not using any strange technology. It's just pure CMOS, 28 nanometers, TSMC, which is strange in this world that somebody is doing for optoelectronic component just with pure CMOS at this speed. That's something that we are forced to do because if we want to go to automotive industry, we cannot use fantastic or very nice technologies. We have to adopt main technologies like pure CMOS because they are the only ones qualified for automotive applications. The package is a revolution in some way because it's the first time that a plastic package is going to be used for optical communications. The ferrule is going to be, if you remove this white part, which is the dust cover, you can put the ferrules of the connector just in the package. I cannot show pictures of the connectors because it's not of our own company, but we are collaborating with several connector companies in order to develop the connectors which are a snap fit on top of our transceiver. And the header connector is just plugged in our transceiver. The transceiver is a BGA component which is soldered in the PCB. It cannot handle the stress of the connector. So one of the difficult parts here is how you can align a connector which is going to be plugged by a person with fingers very big and used to connect typical automotive connectors, which I have seen in the assembly lines people tearing the wire harness with the two hands, and they are making huge forces. You need to handle all that, and the fiber is directly connected to the package. In order to do that, we have to develop with the connector manufacturers a concept where the connector mechanical stress is directly transferred to the PCB and to the enclosure, but not to the transceiver, because if you transfer that to the transceiver, you destroy it for sure. And it's not easy. And this is also what we are doing when we develop the package. We are also developing the connectors solution for the industry. And also what we do is, in order to be able to manage all the temperature range, the tolerances that we are going to handle are huge compared to what is typical for optical communications. So we need to have lens and mirrors inside of the package to make sure that we can align perfectly the pixel and the photodiode with the ferrules and the fiber. This looks like simple, but it takes a lot of hours of engineering, testing, validation. Conceptually, the packages are very simple. The multi-gig is just the CMOS die is going to be flip chip because the huge amount of IOs. And then the pixel and photodiode will be die attached to the substrate with precision of less than 1 micron. And then the lead, which has all the optics, the lens and the mirrors and everything, will just be a glue on top. And that sounds simple, but all the tolerances that we need to manage within all the temperature range and all the lifetime and all the conditions is complex. The other one is simpler because the tolerances of the plastic fiber are huge. We are talking about hundreds of microns. For managing the 100 gigabit, we need to develop new package that is not yet developed. We have to do it. But we want to approach the same philosophy. For automotive industry, you need to provide low cost, very, very robust, fully automated package for the integrated photonics world. And this is what I want to bring here. This is one of the efforts that we are doing. we are going to do it in the project, and we would like also to, if we have success with this effort, we would like to be able to provide to the industry a very low cost, fully automated process of packaging, which I think is something that is needed in the integrated photonics world. In our facility, we are going to be able to do many steps, like wafer processing, die attach, plasma cleaning, wire bonding. That is going to be used for our own products, but as I will tell you later on, we are also offering to other companies because we will have capacity extra. How we are going to do that? One of the efforts that we are going to do is, until now our products have been produced in China. Now we are bringing that to Spain, and we have to compete with China. The only way to do that is trying to do things in a different way, because if we try to do things in the same way, salaries in Europe, as you can imagine, they cannot compete with those in China or Malaysia or whatever. So we try to change the approach. If you look to the current OSATs, most of them, what they have is lines and lines of machines. All of these machines are doing the same task, like wire bonding, die attach. And then you have a lot of people moving trays from one machine to another machine, going step by step. Okay, that is very efficient in the way that you are getting the best of the machine, because the machines are always completely loaded at full speed, but it's inefficient because you have a lot of operators moving trays, at least when you have low volumes. Yeah, so what we try to do is a different approach, which is being used already when you have very, very high volumes, but we want to do it by default, even at the low volumes, is you put a fully automated line with all the steps, one after the other. The trays will be moving automatically. The amount of operators per line is being reduced to the minimum. Of course, you are not optimizing the machines, because there might be machines which are capable of doing high-speed processes, others that they are slower, and the full speed of the line will be the slower one. But on the other hand, you are optimized in terms of money, which is what is important. The main KPIs that we are going to have in this production line is that we want to be able to produce an IC every 3 seconds, which is going to be a challenge, not easy. We want to produce at least 5 million chips, have 5 million transceivers per year. We want to minimize the amount of maintenance stops. As you can imagine, this is really expensive. We are targeting 3 operators per line, and it will be operating in an ISO 6 environment, because this is what is required for the automotive industry. Even when this is not needed for typical packaging processes, we need that. Of course, we are going to have, with a lot of sensors, centralized software, and so on. And then for the future, we want also to optimize not only the amount of operators, but also the machines itself. And the only way to do that is to use robots. And this is a second stage of what we want to do, but it's always nice to present what we dream that we can do. And then I'm going to go fast. We are going to have a lab with a lot of capacity, also with wafer processing, with a lot of capacities that we are offering to the community. The European Union is forcing us to offer that. So it's not because we are nice guys, it's because the spillover requirements of the European projects forces us to do that. We are also offering the qualification process. Going into the automotive is very, very challenging. You need to go through a lot of qualification, thermal, ambient. You need to really carefully analyze what is critical for your component, what is giving you failures. You want to achieve 0 ppms, that's not easy. And this is a draw of all the tests that I need to go through to qualify for automotive applications. We are going to set up a lab which is capable of doing that for our own products. And of course, we offer that also to the community because probably it will help. We have to address very high temperatures, humidities, vibrations, ESD, latch up, everything that you can imagine. Of course, we are going to set up a facility for doing failure analysis, and this is something that we are offering to you. Okay, that know-how will be in our side. And also, due to the fact that we are going to develop this new photonic, integrated photonic package, low cost, robust, targeting automotive applications, hopefully all this development that we are going to do, it can be reused in your initiatives. And well, it's not easy to put hundreds of fibers going into a chip using our approach. But when you have 2, 3, 4 connections, having a low-cost package may make sense. And this is what we are offering. We are already talking with some of you that you are interested. But for the rest of the people, that's what we are offering. And that's my presentation. Thank you very much.
Okay, thank you, Carlos. Very interesting. Any questions from the audience?
Yes, so you probably have enough with the automotive industry, but there is something interesting in the medical domain. There is very similar approach. So fiber, big, LED, big, to extract data from catheter. So there are something like the same data rate that you are talking about now, right? Is it something I know Cars is already taking a lot of your time, but is it something you would be interested in? I mean, Philips is running programs on this, so being able to extract data, very similar approach, fiber in, fiber out, getting the information, LEDs. Yeah, I mean, I guess all the elements are there, right, mostly. But then it has to be on a catheter, right, which is another headache in terms of qualification.
We have customers in the medical environment that are using our approach, not Philips. But we have Japanese customers that they are making products with our solution. And they are reusing all these development of low-cost, high-reliable products for the automotive in other markets. They are getting benefit of that. And of course, we cannot develop something specific for the medical environment because typically they don't have enough volumes. But people are taking benefits of what is developed for the automotive. Sure.
Okay, any other question?
Hi, thank you, Carlos. I have a question for your product, Lopez, it was called, I guess, the Pixel One approach. How do you envision, how you are going to tackle the thermal budget that you need to accomplish? Are you allowed to have active temperature compensation, or is on the package side?
No way.
How do you get a Pixel to lace at 110 degrees? That's the question.
Okay. Well, that has two parts to answers. One is how you dissipate all this power. We are developing our package, and of course, we will try to dissipate all the power generated by the CMOS die to the substrate and to the PCB, trying to avoid heating even more the pixel. Pixels has been the main problem of the standardization. We started with the 150 nanometers pixels, and that was the initial idea in the standardization body. But when we went in collaboration with Photonics, when we went through the failure analysis of that, we put thousands of pixels during HTOL tests for many, many hours, 500 hours, 5,000 hours. They fail. We did the analysis with them, why they failed, and it's intrinsic of the 850 nanometers, I think. So we shifted to 980 wavelength, and the standard right now published is 980 nanometers, which is unusual in the communications. The main reason is that we are adding indium into the pixel, which really gives a lot of stability and after more than 2 years of the pixels being operating in thermal environments, they didn't fail, any of them. So we are pretty sure that the technology that we are using, the pixels, are the right ones. We need to shift the wavelength to be able to achieve that. And it has been one of the key discussions we had in the standardization bodies, because Broadcom and others wanted to use 850 because they know they have the technology and they want to reuse it, but we are using the same pixel type that is used in mobile phones for the face recognition, which is 940, but we moved to 980 in order to be able to do flip chip also in the pixel, because in 980 the wafer is transparent. So we may be able to do this flip chip approach, which allows us to have better alignment in the packaging. It's not going to be done like that in the first iteration. In the second iteration, we wish to do that. So that's why we select 980, because reliability and because it's transparent, the wafer to that, and we can do flip chip. So it's a key part of the technology that, and it's in collaboration with Photonics. More questions?
Okay, thank you. Yeah, one last question. I was interested in what kind of volume do you need to have before you can access your packaging, let's say, services?
Well, we will have a prototype lab, which volumes are tens, hundreds, even thousands. But then for our production line, we need to have 100,000 or even 1 million, because otherwise setting up that line. Maybe that line can be shared with other projects, and doing a small tweaking of the program, we can produce several products, and you can add all the volumes. But at least for the prototype, we can do thousands, I think.
Okay, thank you. Then let's thank the speaker again.
Okay, so we came to an end 1 year more. I won't make it long. Lunch is waiting. I only want to thank you all the exhibitors, sponsors, and attendees for this event once more, and hope to see you next year again.